it's showing up on his laptop. It's just the streaming station for some reason doesn't want to show it here as well.
Yeah, like I'm seeing, I'm on a separate computer, I'm seeing test, test, this is capture, test, 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 test.
Yep.
Do you guys have any quick and easy way to share a raw video feed with me that's live, like whatever you're broadcasting? Can you share it via Skype or something so that I can actually see the slides as they're flowing through them?
I mean, we could try to set up a second stream through.
That's a bit of this
And YouTube doesn't do anything for me because it's so delayed that I have to see it. I have to see the words and then I have to see it before they say it.
Yeah. Yeah, this is gonna be tricky because I don't know if it's gonna kill our system.
Don't worry about it. If you haven't set it up ahead of time, you know, I've worked with consulting other venues and we did it way ahead of time on another job. And yeah, bug now probably.
Yeah.
I mean, I'm using it, I tend to be, I'm using it to watch the stream, monitor the stream, yeah.
Yeah.
We're introducing just a second one, 3.5. Hi Stacy, it's Paul Shea that joined the conversation.
It's Paul Shade's here.
I'm just joining the conversation on the idea of giving you a separate
Yeah. I think we should start. Where'd Barbara go? Oh, hi, thank you. Okay, I think we're ready to get started.
All right, hello everyone. So it's my pleasure to introduce Dr. Barbara Sarnica. Dr. Sarnica did her graduate work at University of Michigan working with Susan Gelman, and then she spent a brief time at Harvard with Susan Carey, and now she's an associate professor at UC Irvine. And her work is just amazing. You'll get to see in a second. And of course, she's gotten all kinds of awards for that, like the NSF Career. And just a little bit ago, we were walking, and I asked her what the highlight of her career was. And she told me that she's been featured on the Savage Lovecast, which is this podcast that brings in scientists so people can ask them their questions about sex. So please join me in welcoming Barbara Sarnica.
No sex in this talk, I'm afraid. Okay, so when I was looking over the schedule, I saw that a lot of people here don't work on numbers, so I thought I should give a 1-minute introduction to number. So brace yourself, here you go. Human beings have a primate brain, and primate brains can track individuals, so we can say like this one, that one, another one, not the same one. And we can also represent approximate numerical information. So if we see a bush with berries and another bush with other berries, we can say, like, I think there's more on this bush than that bush. Maybe there's about twice as much. And human beings also have, of course, a special talent for building tools. So if we have to carry a lot of things in our hands, the thing that makes humans really, well, a thing that makes humans really different from a lot of other primates is when we get too many things to carry in our hands, we might come up with some cool solution like building a jar to carry more things than we can carry in our hands. And in the same way, I think exact numbers, large exact numbers, are tools too. So maybe you can keep track of 1 sheep or 2 sheep or 3 sheep. You got a few sheep, you can kind of remember them, you can see if they're all there. But when you get a lot more sheep, it gets too hard to carry them all in your mind. And so you start doing something like making notches on bones or putting pebbles in jars to try to keep track of things. So I think of exact numbers as tools also. When you fast forward to people like us, adults in numerate societies, I have a different metaphor for you. So the way I think about the relationship between math, all the things we do with numbers, and of course math has a lot more than numbers in it, but let's think about math, and the approximate number system is like this. The approximate number system, by the way, is that approximate magnitude, more berries on this bush than that bush kind of system. So here's how I think about it. Math is like ice hockey, and the approximate number system is like cardiovascular fitness. So if I ask you, if you play a lot of ice hockey, will your heart get stronger? Yes, sure. And if you're an ice hockey player and you add cardio training to your workouts, will that make your ice hockey better? Yes, of course. Then do we say that cardio fitness causes ice hockey? No, right? That's kind of necessary, not sufficient. Like, we wouldn't really say that. And more to the point, Mexico has never won a medal in any Olympics in ice hockey. Now, do we think this is because Mexicans have poor cardiovascular fitness? No, right? So the fact that you can change one thing and it affects another thing doesn't mean that the second thing is just an elaboration of the first thing, right? Okay, so how do we acquire this system, this ice hockey and cardio fitness numerate tool system? Very briefly, these are what I think are some pretty well-attested steps in developing a counting list representation of the positive integers. Now, math people will stop and say, wait, there's a lot more than positive integers in math. And I would say, yeah, not only is there more than positive integers, this is not even the last representation of the positive integers that you will need to develop in order to become numerate adults like us. But this seems like the first kind of verbal exact number representational system that kids acquire. And it seems like, from what we can observe, they first learn to count. So that's just saying 1, 2, 3, 4, 5, 6, 7, 8. And then they learn also to point to one thing while they're counting. And then they connect, and this is a very big question about how they do it. They connect small Subtizable set sizes like 1, 2, 3, and 4 to individual number words. So they learn that 1 means this many things and 2 is this many. All the way up to 4. Then they learn the cardinality principle, which we've talked a lot about. So the cardinality principle is where you understand that if you go 1, 2, 3, 4, 5, 6, 7, and you grab one thing for each of those number words, that 7 is how many things you have in your set. And just to make it really clear, cardinality, understanding the cardinality principle is not the same thing as knowing how to count. And I have a beautiful example of this right here. Come on. Okay, and I apologize for the video quality. This is Emily Kerrigan, who was in my lab, and then Maria Coppola's lab, and is now in North Carolina doing this given number task.
Can you give him 5? Is that 5? Yay! Can you count and make sure it's 5?
1, 2, 3, 4, 5, 6, 7, 8.
Can you fix it so there's 5? Is that 5? Yay! Thank you.
You might think it's confusing that we cheer when they give us the wrong answer, but American children need to be praised for everything they do. If you don't praise them, they think you're angry at them and they've done something wrong. So every time they respond, we are delighted. Okay, so just to let you know why I think knower levels, number knower levels, are a better way to look at kids' performance in these tasks than their age, which is a typical thing we do in developmental research. We'd say 2-year-olds do this, 3-year-olds do this, 4-year-olds do this. Here's an example of a task where the results look really different when you look at the age versus the knower level. So if you're a child in my lab and I'm doing this task, I would put a stuffed frog and a stuffed lion on the table and I say, I'm going to tell you a story about when Frog and Lion came to my house and I gave them some snacks. And I tried to make their snacks just the same because they like their snacks to be the same. But sometimes I made a mistake and their snacks were not the same. So I'm going to show you their snacks and I want you to tell me if they were the same or if I made a mistake. Okay? Here's Frog's snack and here's Lion's snack. Now, are they just the same or did I make a mistake? You say, you made a mistake, and I go, oh, I made a mistake, I can't believe it. All right, and then I take the snacks away and I say, now Frog had 6 peaches. Did Lion have 5 or 6? And you answer me, and then just to make sure you remember, I say, and were they just the same or did I make a mistake? All right, so when we look at the results of that task, here's what we find if we just plot age against performance, right? So you've got the kid's age on the x-axis and on the y-axis the proportion correct. And like it's, okay, they clearly do, older kids do better. There's nothing very surprising about that. But if I replace those little blue blobs with like a 1 for 1 knower, 2 for 2 knower, 3 for 3 knower, C means cardinality knower, P means pre-number knower, then you see this. Really, really different. And if I summarize those in a box and whiskers plot, you see this, right? So it starts to look like age hardly matters at all. What really matters is whether they understand cardinality or not for this particular task. But notice, you don't have to, there's nothing about the cardinal principle you need on this task. We don't let the kids count. They don't have to know that counting per se would lead to that cardinal outcome because we don't let them count. We just say, are they the same or not the same? And then we take the pictures away. Is it the same number or a different number? All right, so this is just to make you, to convince you that number knower levels are an important measure of their sort of conceptual understanding of the verbal system. So then we get to the question that we're all interested in here today is sort of like, how is the linguistic number system, the symbolic number system that we use in counting and when we use number words and we write numbers, how is that related to the non-symbolic, innate, approximate number system and object-based attention, individuation, all the stuff that's not learned and not verbal? I would say one possibility is that I can't advance the slide. Come on. is that language, you could think of language as a lens in some cases. So language, it's not that you can't perceive numerical distinctions, but if they are continually marked and pervasively marked in the language that you're speaking all the time, this might draw your attention to a dimension of experience that you might otherwise ignore. So one kind of evidence for this is a study from a long time ago now, about 15 years ago, that I did with colleagues in Russia and Japan, where we were asking whether kids knew one. So this is a bunch of kids, average about 2.5 to 4.5 years old, and we just asked what percentage of them know what the number one, that the number one means this many. We looked at Russian speakers, English speakers, Japanese speakers. Japanese does not pervasively mark singular plural. Russian and English both do. We looked at how many kids knew two. You can see it's still higher in Russian and English than in Japanese. And similarly, when we looked at how many kids knew three, still higher. So, of course, there's a lot of reasons that kids might learn one sooner in St. Petersburg and Ann Arbor, Michigan than they do in Kyoto. But it has been replicated a couple of times. So children speaking Mandarin Chinese also learn one later than children speaking English. And children speaking dual marking languages, Slovenian and Saudi Arabic, learn two earlier and three later than kids speaking a bunch of other languages that they looked at. So it seems like there might be something there, right? That the grammatical number system might play some role in drawing people's attention to these distinctions between one and more than one, or between one and two and more than two. Another kind of evidence comes from, this is a study we did a few years ago in my lab, where we were looking at whether there was a relation between kids learning the verbal number system and just paying attention to numerosity, again, as a dimension of experience. So we showed kids a card like this, and it said, depending on the trial, we might say, well, this is a picture of orange turtles, or this is a picture of happy turtles, or this is a picture of 4 turtles. And then we'd show them 2 alternatives and say, show me another picture of orange or happy or 4. So they had to match on whatever dimension we gave them. So this looks like an area versus number match. So there's either a picture where the area covered by turtles is the same, or a picture that has the same number of turtles. And so if I said, this is a picture of 4 turtles, show me another picture of 4 turtles, obviously you should pick this one. And what we found was that when we asked kids at all number knower levels, 1 knowers, 2 knowers, 3 knowers, 4 knowers, and cardinality knowers, when we asked them, show me another picture of happy turtles or show me another picture of orange turtles, they did really well. But when we asked them to show me another picture of 4 turtles, they didn't do very well at all unless they understood cardinality. Or more to the point, the more number words they knew, the better they did, specifically on that number task. So it wasn't that they couldn't do the task. They could match color, they could match mood. But when you had to match number, it really made a difference how many number words you knew, which seems, again, kind of weird because you don't have to count. There was always more, right? There were always more than 4 turtles in all of these. It was either 4 versus 8 or 8 versus 4 or 5 versus 10 or 10 versus 5. You know, the difference between knowing 2 and knowing 3, it's not clear how that would help you, except that you have to just pay attention to number as a dimension. And these are approximate things. You don't have to count to see the difference between 5 and 10. All right, so in recent years, I have been moving on to real preschoolers, the real preschoolers of Orange County. This is my new funding idea. I was thinking, you know, if my research is spun as a reality TV show, maybe with the present administration, this is going to work better. All right. So what is not funny, actually, is the situation that these kids are in. So very quick, a minute of background on these students. As of 2015, 1 in every 4 American children is Hispanic. About 2/3 of those children live in poverty. And Hispanic students lag at least half a standard deviation behind their white and Asian American peers in mathematics at the beginning of kindergarten and throughout K through 12 schooling. So there's a huge SES-related, socioeconomic status-related math gap, particularly affecting these kids. And so we did a big study over several years that looked at low income, low socioeconomic status dual language learners. There were 263 kids in that group, and then we had comparison groups of low-income English only, not low income, I should say. Graduate students have low incomes and very high-performing children. This is low socioeconomic status, so parental education, low, income low. And then high socioeconomic status English speakers and dual language learners. We were interested in whether being bilingual, being a dual language learner had any important effects on math development. Spoiler, it does not. Okay. So then we ran into a different problem because we wanted to measure, in these kids, we wanted to just, as a basic thing, do a bunch of number battery tasks and find out where does this gap start? Like on what measurable tasks that we can do with preschoolers is there this gap between low SES kids and high SES kids? Where can we, because it's already there by kindergarten. By the beginning of kindergarten, the gap is already there, and all of the variance that you see later on is traceable to that original gap with different growth models, or different, trajectories of growth, but it all comes back to that gap. So really, if we want to understand this gap, we got to look before kindergarten. So we're thinking, what can we do with preschoolers? Well, an obvious question, we asked a bunch of questions, but the one I'll focus on here for this talk is there a gap in their approximate number system acuity? Is it a problem with the perceptual system? Or is there a gap in their learning of the symbolic number system, the linguistic number system? But then we run into another problem, which is that several studies have reported a correlation between children's number knower level and their ANS acuity, which would imply, I just reported, gosh, I realize this could be confusing. I just reported that there's definitely a correlation between their number knower level and their attention to number as a dimension, but that's different than your perceptual system being better at telling numbers apart, right? So what studies have reported that we think is suspect is that kids' actual ability to distinguish different numbers is better as they know more numbers. So the problem is, if you get those data, if you look at the data, they look like this. It looks like chance performance by all the kids who don't understand the cardinality principle, and above chance performance by the kids who do understand the cardinality principle, and if you throw that into a correlation, you get a correlation. But we thought that was a problem. And then we started looking at the way we measure approximate number system acuity in preschoolers. And what we typically do is we show them two clouds of dots and we say which side has more dots. Or we show them blue dots and yellow dots all on top of each other and we say, are there more blue dots or more yellow dots? But if you think about this, using this example of the separate clouds, which side has more dots? Let's just imagine for a minute chocolates. I just like to imagine chocolates whenever possible. Let's imagine that instead of the word dots, you're using the word chocolates. So you say to the kid, which side has more chocolates? They're supposed to pick this one, right? Because they're supposed to pay attention to number. But if they heard, as I would, which side has more chocolate, they would pick this one. So you're relying on like 3-year-old children to hear that S on the end of the noun and understand that it indicates count syntax and they're supposed to count and they're supposed to pay attention to numerosity instead of area. It's kind of silly, right? Like, how do we know they even understand what we're asking? So we started doing training, and I just found out that Liz found a much better way to do this, so I'm going to get the protocol from Liz afterwards. But we started doing training where we showed them the task, and then it was very easy ratios of like 1 to 3, and we would give them feedback when they got it wrong. We'd say, well, these dots are bigger, but this side has more dots. See, they're smaller, but there's more of them. Again and again and again, and we did this until the kids got 8 trials in a row correct. So what we found was that out of 490 children in the study, we got valid ANS scores for only 61% of them, right? Because 158 children did not ever get through the training. They either refused to play at all or they quit before they got through the training. 33 others didn't score above chance, so they got through the training, but they never got above 56% on the test trial. So even if chance is 0.1, they're not better than chance, so we can't trust that they're doing anything that we can measure. But among the children who did complete the task, older children performed better. That's not surprising. There was no difference between dual language learners and monolinguals. Again, not so surprising. High SES kids did perform better than low SES kids. Maybe there's something there. How much better? The inferred mean coefficients of variance in these data were 0.47 for the low SES kids and 0.42 for the high SES kids. to give you a sense of what that means, if you and I were given a task and we were shown a cloud of 50 dots, if you had a coefficient of variance of 0.47, that means you would guess between 26 and 73 dots. If you had a coefficient of variance of 0.42, you'd guess between 29 and 71 dots. Meh, right? It's kind of underwhelming, right? It does not seem like the kind of difference that could explain the massive differences in math achievement that we see in these populations. Okay, but look at the difference in number word knowledge. So this is the breakdown of knower levels among the high SES dual language learners and the high SES monolinguals. About 80% of them understood the cardinality principle by age 4.5. In the low SES monolingual English speakers, it was about 35% cardinality knowers, and in the low SES dual language speakers, 24%. I think that difference is because the low SES English speakers' parents were a little more educated and they had a little more money. So they were lower, the dual language learners are actually lower SES. Most of their parents had not finished high school and they were living on under $10,000 a year. The low SES monolingual group, most of the parents had finished high school but had not done college. Okay, so conclusions. Ted is telling me to stop. The narrow conclusion is that the huge SES gap in math achievement probably does not stem from differences in perceptual approximate number system acuity, but from differences in children's early exposure to the symbolic linguistic number system. But to study this, we have to use truly non-linguistic measures of ANS acuity, right? If the measure itself requires language understanding, then we can't tell what's linguistic and what's not. Linguistic, I just invented that. But the big conclusion, I think, for all of us coming up with cognitive theories is to beware essentialism, right? Essentialism is this type of reasoning where we think if something is innate and it's invisible and it's inside of us, then it must be causing everything we can see, right? So the ANS is inside of us and it's innate and it's invisible, and so it must be the cause of everything that we can measure in mathematics, and that's the wrong way to think about it, I think. Just because something is inside us doesn't mean it's more important than everything that's hitting us from the outside. Okay, I'm done. What do you want me to do? Yeah.
2 slides. Sure. Cool. I don't actually really have slides, so I'll use them in a bit. Well, first of all, thank you for that awesome talk. And I think that trying to do serious progress in translational work is both super rare and super difficult. And we usually leave it for people who are not primarily trained in science. So I think it's super commendable that Barbara's trying to figure out what exactly is the difference between these kids who are lagging behind in number. And because we often don't engage in that, we end up getting things like Lumosity that are making these games that will train your brain and they're going to make us smarter. And we know that they don't work, but not everybody knows that. And the key thing is that there's this huge leap between something like a correlation or a study that's an intervention that's having some kind of causal relation and an intervention that's actually practical in the real world. And I think in Barbara's talk, this leap, she made it very clear for us. So in the case, even if we have a correlation between the approximate number system and exact math, it doesn't mean that it's something that we should just get excited about and start trying to apply it to the real world. But I think that's where we want to go as a field. We want a cognitive science where we can generate new interventions that are better than the ones we come up with when we just rely on our folk theory of teaching. And the key thing is that we're not there yet, and I think this talk was a very good reminder that we're not there yet. But in the case of numbers specifically, the problems that Barbara discussed run even deeper. Because it's not just the case that maybe trying to train children on the approximate number system will not give us any benefit on exact number. She gave us reason to wonder what is exactly the nature of this connection in the first place. And so when I learned that Barbara was going to talk about this, I decided to take a look at, try to figure out what does the literature look like? Why is it that right now we believe that there's some kind of connection? And right now you can think about it, I find it easy to think of the space of possible theories as having two ends. On one end is this idea that the approximate number system and exact numbers really share some kind of representational overlap. And I can give you two examples of what this might look like. So one idea is maybe the approximate number system really has at its core some kind of exact representation, and then you have uncertainty on the top. So maybe these curves really represent integration over a lot of hypotheses of the exact number, and then counting is this kind of cultural tool that allows you to shave off the number out of this uncertainty, but really in both cases you really are triggering some kind of shared representation. Another way this could happen is maybe the approximate number system is really fundamentally not referring to exact numbers, but then number as a cultural tool imposes these categories on top. So one rough way to think about it is kind of like color, that when we perceive color, we think of it as being very continuous, but then culturally we can break it down into these categories. And these categories don't necessarily need to be totally invented. They can still have some relation to biological cultural constraints, which Bebel is actually going to talk about later. And then on the other end, so that's one end. The other end is this idea that maybe exact number and approximate number representations are totally different things, and they just happen to refer to the same thing in the world. And the question is where in this space of theories does the current evidence point to? And my reading of the literature is that it seems to suggest that there's some kind of shared representation. And it largely comes from three kinds of studies. The first kinds of studies are these correlational studies. So we know that people who have better ANS acuity tend to be better at doing exact math. And this happens both with simple arithmetic and with learning number, widths, and counting. Then there's the second kind of pillar of research showing intervention studies. So if you train children or adults on the approximate number system, they very quickly gain some advantage in exact number. And then there's this third pillar of research, which comes from these older studies that are really neat, that show that when you ask people to think about an exact number, they seem to always trigger this approximate representation that people have trouble suppressing. I'll tell you more about the details in a little bit. But what what I took from the talk is that she gave us some reason to wonder what's going on with those correlational studies. So maybe they don't mean that there's a deep connection between approximate number and exact number, but then we have the problem that we're left with these other two threads of research, and we run into the risk of having a set of studies with no coherent theoretical framework to make sense of. So what I wanted to do is, I think one thing that this talk prompted me was to think about how strong is the evidence from the other studies to claim some kind of shared representation. And just to be clear, the authors of these studies didn't have as a goal to claim that there's a shared representation. So the studies, independent of whatever I say, they have a lot of merit. I'm just trying to ask, if we want to make a case for shared representations, how strong is the evidence? And so correlations are out, and then we have the intervention studies. And so the intervention studies, again, you train people on the approximate number system, and very quickly they gain an increase in exact math. And one thing that you might say is, well, that's easy, it's probably just a placebo. You're training them on something that's math related, then you're doing another math related task, so of course you're going to get a boost. But as it turns out, Molly already thought of that, and she ran a study and showed that that's not the case, so that can't be it. And so there's clearly something going on in those intervention studies, but it still seems that you could have this boost without having some overlap in representation. And again, I'm not committed to this idea, but I can give you an example. So maybe at the approximate number sense, what it does is this kind of error correction of your exact math. So suppose I'm a child and I have to add, let's say, 55 plus 56. So that's 101, but I'm doing my math and the 1 carries over, and then I get something confused and I end up getting 11. In that case, it could be the approximate number system says, wait, hold a minute. There's no way that 55 plus 56 is going to give you 11, and then you're like, okay, I better do this again. So it is possible that you can get these interventions without actually them sharing any representation. Which gets me then to the third pillar, which I think is, I love these studies. And the reason here to just show you. So the task, this is a very neat task. So basically, all that happens is I show you two digits. They represent exact numerosities, and I just ask you which one is larger. And then I measure your reaction time. And presumably, there shouldn't be any effect depending on what numbers I show. They're always exact numbers. You just need to do the same thing. But as it turns out, your reaction time in these tasks varies as a function of two things. The first effect is the closer the digits are together, not spatially, but numerically, people become slower. So people are slower at telling you that 8 is larger than 7 relative to 9 versus 6. And the second effect is that people get slower as you go up in number. So people are a lot faster at telling you that 2 is larger than 1 than at telling you that 9 is larger than 8. And when you think about it, those are exactly the two signatures of the approximate number system. So some people have used that to say, well, this probably means that really exact number is built on top of approximate, to the point that if you think about an exact number, it triggers this approximate representation that interferes with the task. Again, I love this study. What I would have loved to see is what happens if you do the same study, but you switch the numbers with alphabet letters. So suppose I ask you to judge which letter comes later in the alphabet. I don't know if this is true, but to me, I feel like I'll be a lot faster to say B comes after A than if you ask me which one comes after N or O. And similarly, the farther away they are to each other, that might actually speed up my response time. So again, this doesn't necessarily need to be the case, but I think it gets back to questioning whether how strong we can make the case for representational overlap. And going back to Barbara's talk, I think at the end, what we really need is more nuanced models of how cognition and culture interact in the case of number. And my second last thing is just I think that number is the perfect domain to study that because it's limited, but it captures all of these interesting things that happen. So as Barbara told us, it has this system that we share with species and cultures, and then we have this cultural input that builds on top of it. So that was just opening to questions. Thank you. Yeah, I'd love to hear your thoughts on like how the approximate number and exact number share any kind of representation or don't.
So what do I think the relation between them is? Yeah. Did I show you my ice hockey slide? So that's not correlational evidence. Those are causal studies I was talking about. If you change one, the other one changes too. That doesn't mean that that one is just an elaboration of the other, right? So I think that exact approximate number representations are absolutely engaged whenever we think about numbers. Well, I would say up to several hundred. Like there's a point where numbers become completely abstract, and you're talking about, you know, even positive integers become completely abstract after a certain point, and certainly lots of other kinds of numbers are not related to any kind of magnitude representation. So imaginary numbers, you know, it's completely abstract. So, but in the range where they are tied to magnitude representations, which is to say from 1 to something in the hundreds probably, I think every time you use a number word and every time you think about magnitudes, you engage that system. But that's not to say that the best way to improve your use of your performance in math and your understanding of that system is to just tune up the perceptual system that gets engaged. That's what I would say.
Thanks. That was both really, really interesting. I wanted to ask about individuation, which went by on a slide really early, and the approximate system and what kids are thinking that adults might mean when they say the word more. So you gave one interpretation with chocolates. So Jelena Markovic and I have done some work on agreement in Serbian with adults that allows in certain constructions either singular or plural agreement on the verb. And we find that in cases where there's less individuation, so like many foxes compared to only several foxes, where there are fewer foxes but they're more individuated, people are more likely to use plural with the several, fewer but more individuated than they are with the more tightly bound set of dots or foxes or something. And so it made me think about individuation being an important but understudied perhaps aspect of the approximate number system there. And if kids have that underneath their cognition for some set of times, when an adult is saying more dots and individuation is something important there, are they answering the adult-like question of what more means, or is there some individuation aspect to some kids' answers in some children, or in some situations, some cultures sometimes? Do you have a thought about that?
Well, so, I mean, so your example from Serbian reminds me of Russian, which I almost can never tell people
they are
this
like
example.
That. Yes, Slavic
this is a
languages
room full
in
of people that will actually appreciate this little tidbit of knowledge, this little factoid, is that in Russian, well, some people already know it, but in Russian, if you say one, then the noun that follows it is in the nominative singular. So like chair is stool, so you'd say один stool. And if you say 2, 3, or 4, then the noun that follows it is in the genitive singular. So it's like saying it's 2 of a stool, 3 of a stool, 4 of a stool. It's like you're keeping it as an individual and multiplying it, but only up to 4. And then if you say 5 or any higher number, the noun that follows it is in the genitive plural. So it's kind of like, we seem to, in that small individual range, we seem to track individuals if they're sufficiently different from each other, and we can kind of keep track of them with our working memory constraints. And then at a certain point, we just treat it as kind of a mass of things or a combination in number. It's like we know there are individuals in there, but we can't quite track them as individuals. So I always think of it as like when you take kids to a park, if you take like 3 kids to the park, you have to watch the actual kids you took there. You can't just like watch any 3 kids. And then when you leave, you can't just be like, I brought 3 kids, I'm taking 3 kids home. Like, it's not like a representation of the cardinality that you have to keep in your mind. It's those actual individuals that you have to keep in your mind. So I think like Liz would say, for example, I'm pointing to Liz as the person who in this room probably who's done the most work on core number systems, that we have both. We have an approximate system that deals with magnitudes that are not exact, and then we have object-based attention and individuation capacities, and to make exact large numbers, we got to put them together somehow.
I was thinking a little bit about your point about language as a lens by which you can see the world, and I was wondering if you could comment a little bit about kind of the different contributions of the dual trio markers that you get in Russian versus something like the count list. And so like, kind of like, I mean, they're 2 very different formats of representation. You know, with the markers, you might get something like the noun for free along with the set versus the count list, which kind of goes on, might give you something else like magnitude that goes on. So I was wondering what you thought about kind of the trade-offs between the 2 or whether they work together in conjunction?
I mean, if I hadn't done the study I showed you that showed that kids learned number words sooner when those number words were reflecting numerical distinctions that were marked grammatically in their language, then I wouldn't believe it, right? Like in some alternative world where somebody else did that, I'd be like, no way.
Yeah, so then I guess like, right, you know, they're very cool in that sense. But I guess like, what are they learning though about numbers? So they're moving through the subset stages a little bit faster, right? Yeah, so they're able to pick out the exact numerosity in the give n task a little bit better. But I guess, do you think then that gives them something about kind of a broader intuition about how integers work?
About how integers work? No, because I don't think they have concepts of, I mean, not in an explicit sense. They don't, if you said what's an integer, they'd have no idea, right?
No,
so,
not
but I think like, you know, Mathieu Lacour and Susan Carey have this enriched parallel individuation theory that might be on the right track, where there's some state of the nervous system where you are tracking 3 things at once, and there's single cell recording data from other animals that shows we probably just have brain cells that respond when we're looking at 1 thing and 2 things and 3 things up to, again, about 5. So there is some state of the nervous system that is common to those. There's some bunch of neurons that are firing when you're tracking 3 things. And if you can learn to bring that above the threshold of awareness and put a number word on it, then you have a concept for 3, right? Now, how that happens, I don't know.
So I was really interested in your story about Russian, and I hadn't thought about it that way. And it's interesting. I was trying to reconcile it with what happens after 20, right? So that would be a great story if it was actually the case that all numbers 5 and above are genitive plural, but of course it's not. Right?
No,
and
it's
starts
the
over.
last, right? It's a grammatical agreement. So if you say 21, you treat it like a singular.
Yeah, exactly. So how does that square with the story that you were telling about the...
Terribly. That's why I didn't tell it. I didn't tell that part. Yeah, it totally contradicts it. Yeah, I don't actually think that Russian speakers are walking around thinking deeply differently about numbers because they do that. I just think it's sort of interesting.
Well, I'm going to introduce Liz.
Okay.
So, this is, it's not going to be very long though, so we can prepare. So this is one of our most prominent cognitive development psychologists in the world. This Philke, he's worked with a lot of, I guess, collaborated with an awful lot of people who worked on remote cultures, including our group, but also with Stand to Hand down in the Munduruku for many, many years. I guess you're going to tell us about some of that work. Am I right?
If I can get this to work. It's not showing up on my screen, though.
Well, that's a different problem. I don't know.
Maybe I don't need it to show up on my screen if you don't need me to look
There
at
you
you.
go.
Oh, did you get it on the screen?
No, but that's like, it probably has to do with your display. Right? Well, if you go back to that
Mm-hmm.
and change your, you want to change your,
Sorry, I checked it before and it was working, and now it's not.
just go to the top corner, you know, the system preferences.
Sorry. No, see, I think it's the computer. It's getting a little old and feeble, like
There you
me.
go. So you want to go to here? What do you want?
I don't know. It was working a minute. It was working.
Arrangement, display.
But I think the arrangement was right. You know what? I can do it.
right.
I can do it just looking at this. It'll be okay.
You want a mirror?
Yeah, I do.
Okay.
It's working? Do mirror? Click mirror.
You want off though? Do you want a mirror? You want a mirror. She said
I
she
want to
wants-
be able to see it on my screen so I know what you're looking at. Uncheck it. Uncheck it where?
Uncheck it right here. There, now if you just hit your thing, play.
Yay!
That's what you want, right?
Yes, okay, thanks. All right. Molly and I seem to have found ourselves in a group of papers on number, but I'm kind of greedy and I want to talk about both number and geometry. Because I think there are interesting parallel questions that are raised in these two cases, and the answers to them may be interestingly different and may call on language in interestingly different ways. So that's my reason for wanting to talk twice as fast and give you two 20-minute talks in 20 minutes instead of one. So the first one is on this question, the same question that Barbara was talking about. Where do the so-called natural numbers come from, the positive integers? Where do these concepts come from? How do they arise in our minds as children, and how do we reason with them as adults? And then the second set, it looks like the simplest concepts that we have intuitive access to in geometry are the concepts of Euclidean plane geometry, and Lara already talked about Plato and you know, this kind of compelling intuition that if any of our spatial concepts are innate, it's probably those. But where do they come from? How do we grasp them? Are they in fact innate and universal or not? And if not, how do they develop? And what I want to suggest is that both of these questions are wide open right now. One can make good arguments for any number of incompatible answers to them. But I think it's interesting to consider them in the context of this workshop today, because I think work on people from remote societies may play a really important role in giving us evidence that will tell us the answers. So let me start by giving you one slide on where I'm coming from. When I have questions, I tend not to go into the Amazon to ask, or Australia to ask people there. I go into the lab and I ask infants what they think. And studies of infants, I think, provide evidence for very early developing, probably innate, probably universal abilities to represent aspects both of number and of geometry. Barbara's already talked in her talk and in the discussion about two different kinds of representations we can have that give us numerical information. One representation focused on individuals, especially individual objects, and the distinction between events that involve one object or two or three, and the other, what most people now seem to call the approximate number system, the system for representing larger sets as long as they differ by a sufficiently large ratio that we can detect that difference at a glance as we can in that case there. I also think studies of infants and young children provide evidence for two distinct systems for capturing spatial information, one of which we use when we navigate through the layout. It's a system that's there to answer the question, where am I or where am I going, and does so by representing absolute distance and direction, where you are in the layout relative to things at particular distances from you and at particular directions from you. And the other, a system for capturing the shapes of objects, a system we use for recognizing objects by their shapes. It's answering a different question, what is this, maybe? It does so by representing information that's not absolute, but rather relative and scale invariant. So the difference between forms that have sides of equal lengths and forms that have pairs of opposite sides of differing lengths and so forth. Relative length in this case, or relative angle if one were given the task of discriminating 5 squares from a non-square rhombus. So these systems, there's evidence for all of them in young infants. It comes from studies that don't involve language or any cultural knowledge. My bet is you could take them to remote societies and ask whether adults have them there, and would find that they do in every such society, and that children would start to develop them there. But this doesn't answer the key question about the origins of our concepts of number and geometry. Are these systems, either separately or together, the sources of those concepts? Now, Barbara argued that they're not, but there's lots of people who think that they are, including people who are active today and who know all of the evidence that Barbara or Susan Carey or I would marshal to say, no, 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 these systems we find in infants can't be all there is to number and geometry. Here are a few of the prominent people in the case of number who think that the systems that we find in infants are really all you need to get to the natural numbers. The idea, the general way in which this is argued is that although it's true that if we look at systems for individuating objects, we see they max out after we get to like 3 or 4, or we look at the approximate number system, we find we can't discriminate things. We don't see the difference between things if they get too close. But nevertheless, it could be the case that, say, the approximate number system is a system for representing number exactly. It's just it operates with a degree of uncertainty, so you don't know if numbers get too close together exactly which number it is that you're looking at. But you have a concept of exact number that underlies it. Now, the reason many of us are apt to doubt that that account is right in the first instance was that we can see, as Barbara said, that it takes children years to learn how to enumerate sets exactly by counting. And Barbara, you didn't mention, but we also know, and we should be deeply puzzled by this, I think, that it takes children years to learn the simple facts of arithmetic. There only are something like 81 facts of addition, and there's lots of redundancy in those 81 facts. Yet it takes kids years to memorize the addition tables, the multiplication tables, and so forth. And even for us as adults, if you want to give adults a really annoying, attention-demanding task, have them count backwards by 3s. Simple arithmetic, conceptually simple, is really, really hard for us to perform. Now, people who believe that natural number is innate have a rejoinder to this. They say, yes, those tasks are hard, but they're hard for other reasons, not because the concepts are hard. Infants may perfectly well conceive of sets of all of the positive integers, the infinite series of positive integers, but not be able to work out how to operate on these by counting or by using symbols like Arabic notation and arithmetic algorithms. Now, to distinguish these views, to test the view that natural number is innate, we need ways of testing for knowledge of number that doesn't involve symbols, algorithms, or language, okay? Ways of testing for number. And I think there are ways of doing that to test for 3 different aspects of natural number that I think are particularly important for us to be looking at. And I'm going to put them all out here because I'm hoping there'll be tests. So people will be inspired to do these tests on people from remote societies. One aspect of natural number is something Veronique Izard calls the principle of exact equality. If you have 2 sets and you can put the elements in one set in one-to-one correspondence with the elements in the other set, then the 2 sets have exactly the same numerical value. A second, which I'm particularly fond of these days, is a principle of compositionality. If x and y, or n and m, are both positive integers, then so is their sum and so is their product. Positive numbers can be combined to form new numbers that are larger than those numbers, but that have the properties of those numbers. They pick out exact numerical magnitudes. Finally, a third property that I think has been studied almost not at all, and insofar as it has been studied, Dave Barner has been starting to study it, it seems to develop very late, is an understanding that within the system of the positive integers, one has a special status. It's the only number that can be successively added to an array, which if you do it long enough and patiently enough, you will get to all of the natural numbers, right? Succession addition of 2, you're going to miss the odd ones and so forth. 1 lets you get to all of them, and it specifies the minimal distance between each number and its nearest neighbors. Now, knowledge of these properties could, in principle, exist without an understanding either of any number words or of verbal counting procedures or of the algorithms of exact arithmetic, and it can be tested for through methods that don't require those things. So let me just give an example talking only about the first of these properties, the principle of exact equality, and I'll talk about an experiment that was conducted by Veronique Izard a few years ago. So what she did is she set up for kids a one-to-one correspondence relationship, following on a long tradition that I think Piaget started, between branches on a tree and finger puppets. So she has 6 branches and 6 finger puppets, and then plays a game with the child where the finger puppets are bored of being in the tree. They want to go into the box, and maybe they're tired, they're going to take a nap. So they put all the finger puppets into the box. And then, together, they decide time to wake the finger puppets up, so they bang on the box. Finger puppets start to come out, and together they put 5 of the finger puppets back onto the box, back onto the tree, sorry. Now, while they're doing this, the experimenter meanly, surreptitiously removes the 6th finger puppet from the box and says to the child, okay, you finish. And the question is, will the child go back into the box looking for another finger puppet or not? And so she measures how long the kid searches in this now empty box and compares their search time to search time on a different trial that's the same in every way, except that the starting number was 5. There was an empty branch on the tree. Okay? She does this and discovers that the kids, these are children who have not yet learned to count. They're about 3 years old on average. She discovers that they tend to search the box much longer when the initial starting number was 6 than when the number was 5, showing that they have some sensitivity to the distinction between that starting state and the 1-1 correspondence between the objects. Now, question, was the 1-1 correspondence actually playing any role here? To see that, she repeated the study with just one change. Instead of starting out with a tree with 6 branches, she started with a tree with 11 branches. So now there really isn't any 1-1 correspondence relationship that the kid could be exploiting, and in that case, their performance falls totally to chance. Okay? So it looks like they're using 1-1 correspondence to reestablish sets of 5 versus 6 elements. Now, do they understand that the sets that they're reestablishing have exact numerical magnitudes? As a first step to get at that, she varied the experiment in the following way. Again, she starts with 6 puppets on the tree, and they go into the box. But before they come back out of the box, she announces one of the puppets has to leave. She takes him out of the box, gets him out of the scene, and then they together return 5 puppets to the box. So we've now removed 1. Do they still expect there to be 6 there at the end? And their response, their searching in the box is compared to that of kids who start out with 5, and when the 5 go in, while they're in the box, a 6th one gets added, okay? So does adding 1 or subtracting 1 change how kids perform in this task? Indeed, it does change how they perform, but they don't perform in a way consistent with the effects of adding or subtracting 1 on the numerical magnitude. Rather, what seems to happen in this version of the task is they just go to chance and start searching equally much or little in the box, regardless of whether they've been given 6 minus 1 or 5 plus 1. Now, Izard wondered, is this because kids are just confused by the addition or subtraction? Is it too much to remember? Is it too demanding? So to see 3, she went down to small numbers and repeated the same experiment, except instead of starting with 5 or 6, she's starting with 2 or 3. And there she gets very robust and dramatic success in this task. So kids who get 2 plus 1 expect three puppets on the tree at the end, and kids who get 3 minus 1 expect 2 at the end, showing that first, small numbers are being treated differently than larger ones, as in the cases Barbara talked about, and second, that for large numbers, adding or subtracting 1 seems to introduce uncertainty for the kids. Okay, so pursuing this a little further, why is it introducing uncertainty? What is going on in these tasks? So Ted started us off today by talking about a wonderful study that he did with the Pirahan, showing that they could create this one-to-one correspondence relationship between batteries and whatever the other things were, right? They could set them up in one-to-one correspondence. And I think the first study I showed you from Izzard shows that these kids can do it too. But how are they representing the sets whose one-to-one correspondence relationship they're establishing? Izzard did one more study to try to get at that. So in this study, it's like the first study in that the starting number is always either 5 or 6. The ending number is always 5. But what happens in between is one of the following 2 events. In one event, a single puppet comes out of the box while they're all in there, and then that very same puppet is returned to the box. Call that an identity transformation. At the end, you've got the same guys that you had at the beginning, but one of them has come out and then been put back in. In the other event, one guy comes out of the box, goes away, as in the previous study, and a different guy who looks just like him and like all of the other puppets who were in the box gets added. Call that the substitution transformation. Now notice that numerically, these 2 events are exactly the same. They both involve subtraction of 1 followed by addition of 1. They're not the same, however, at the level of individuals, and that turns out to matter enormously for these kids. So in the identity case, they succeed. In the substitution case, they fail. Okay? I think an interesting question is whether the Pirahan would succeed in both these cases, or rather show the same pattern as was shown by these young kids tested in Boston. What I think this shows is that the 3-year-olds can represent exactly corresponding arrays of objects, but not exact numbers. They're not recognizing exact numerical equality. They know there's something the same about the arrays when the objects are the same, but not something the same about the cardinal values characterizing the number of elements in each of these sets. So that, I think, is a serious reason to question the popular view that natural number concepts are innate, and that what's hard is just figuring out how to use them, how to count so you can figure out which number to apply in any given case, how to use them in performing arithmetic. So if they're not innate, how does this understanding develop? Barbara's already talked about Susan's influential theory. She argues that we start with core concepts of objects and the ANS, but with no innate natural number concepts, and we construct those in a culturally variable manner by building on the core representations that the infants have, but crucially by mastering a culturally variable cognitive technology, right? Mastering counting. It's by actually mastering a counting procedure that kids come to grasp the logic of natural number, including exact equality and other logical properties of the natural numbers. Now, I think the clearest way to test for this is to go to remote cultures and ask whether people in a culture that lacks a counting procedure nevertheless pass tests for mastering the logic of natural number, such as the logic of exact equality. And that's what Veronique Izzard and Pierre Pica did going into the Amazon to a group that I think lived. They're out there in the jungle somewhere, the Munduruku. They have no counting routine. They have number words, but use them approximately, and not very many of them. They have words for 1, I think they're single words. They might be expressions. They've got lots of syllables in them for 1, 2, 3, and 4. Also a word for 5, which is hand. But they use them imprecisely, and they have no counting routine at all. So Azard devised for them a version of the finger puppets test. And it's actually a particularly stringent version of the test. It was presented on a computer. She's got interlocking puzzle pieces, a row of black puzzle pieces, each of which interlocks with a red puzzle piece, and presented a whole series of problems. Here's an example of just one problem. You start out with the interlocking pieces in one-to-one correspondence. I think there are 10 black and 10 red in this case. Then all the red guys go into a can. And then either nothing happens, or one red guy is taken out of the can, or an additional red guy is added into the can. I think that's what's happening here in the middle left. An 11th red puzzle piece is going into the can. And then red puzzle pieces come out of the can. And at the end, either all of them have come out, or 1 or 2 should still be in the can. And the questions to the Munduruku is, what's in the can? And they get to see the cans turned over, and they have to choose, should there be an empty can? Should it have 1 in it? Should it have 2 in it? So if they can use one-to-one correspondence over changes in addition or subtraction of 1 while the members of one set are out of view, they should be able to succeed at these tasks, and indeed they do. They passed all of these tests for exact numerical equality. Now, this work is unpublished, and the reason it's unpublished is that Azard is a perfectionist, and she's worried about the fact that some of the people in the Munduruku community are bilingual in Portuguese, and the bilingual Portuguese speakers all count in Portuguese. So this study in itself doesn't conclusively show that you can master the logic of exact equality without understanding counting, even though their native language doesn't have counting in it. Fortunately, since I'm out of time, I don't need to talk about Julian's work. Julian, I'm counting on you, wherever you are here, to talk about it, that asked questions parallel to Veronique's in a population where he's in a position to actually assess whether kids understand counting or not. So he will tell you the answer to that. I think I have to give you a piece of the answer. It turns out in Julian's data, as in Veronique's, counting is not necessary for mastery of this aspect of the logic of natural number, the exact equality following from one-to-one correspondence. Now, why might the Munduruku, why might the Munduruku and the Chimani succeed at this task? How could they possibly do this if they're not using a counting routine and they only have a limited number of words? Well, here's what got me really excited about this group, and it was really the work that Veronique did on the Munduruku that has led me to think in a different way about how natural number concepts might develop. So although Munduruku has a very limited number of numerical words, it has the resources for forming expressions that combine those words together. So there's the expression 2 hands, which picks out 10. There's the expression a hand and 2 on the side, which picks out 7. They don't use these terms frequently because they don't talk about exact numbers frequently, but you can elicit them, and you can also, if you present them with those expressions, they will use them. And interestingly, for a hand and 2 on the side, they'll use it exactly. Perhaps in the same way as if I said there's 100 people in this room, I mean approximately 100, but if I said there's 113 people in this room, I probably counted, okay? So this, I think, suggests a third theory, that natural number may be neither a cultural construction, that would vary wildly depending on what cognitive technologies your culture had happened on, nor innate, but rather something that develops with mastery of particular aspects of natural language. If you have a few number words, and if you've got resources for conjoining them together, for saying things like 3 dogs and 2 more, or 3 dogs and 2 cats, 5 pets. You're in a position to develop a system for representing larger numbers that have the exact and logical properties of the smaller ones. So this is a hypothesis, I think, that raises key questions. Are these aspects of language productive in languages like Munduruku? Are they universal across languages, or is Dan Everett right and they're not? Do natural number concepts emerge when children master them, or is there some further learning or a different kind of learning that's necessary for that? Those questions are unanswered, but I think they're answerable through research in remote societies. So to summarize, I think it's possible, we're in a position where there's 3 possible stories, any of which could turn out to be right. Natural number could be innate and universal. It could be a culture-specific construction, or it could depend on natural language and emerge from an understanding of basic aspects of natural language in any people who learn a language that has those resources. And I think it's research in remote societies that can test for that. I was going to give you a pitch for why I think that's the right answer, but I'm out of time, so I won't. I just want to set up the questions for geometry, and then Molly's going to talk about it. I knew I wouldn't have time to actually talk about geometry. But let me just say one thing about the Meno dialogue, because Lara brought it up earlier today. This is the dialogue Socrates had about virtue and also about geometry. So everybody knows the dialogue, right, with Meno's slave, in which Socrates, by simply asking the slave a set of questions and drawing diagrams on the sand, got him to acknowledge that the area of a square doubles with the length of a side multiplied by the square root of 2, if you will, anyway, with the length of in proportion to the length of the diagonal. And this seemed to suggest that Euclidean geometry is intuitive for adults whether they have education or not. Now that suggestion was brought into question by some work conducted by Andrea Goldman and Bariano Sigman, where they repeated the Meno dialogue and discovered 2 rather disconcerting things. The first thing they discovered was that educated people respond no better on the Meno dialogue than Meno's slave initially did. That is, your first pass answer to Socrates' questions tends to be wrong, despite the fact that you studied Euclidean geometry in school. But second, they did something that Socrates never did, which is after the dialogue ended, Socrates asks, "So do you understand?" the slave, and the slave goes, "Yes, I've got it." He never tested him by giving him another square and saying, "Great, make one twice as big," to see whether he would draw the diagonal and then draw a square off that. When you do that with educated adults in Argentina, almost nobody gets it right. Okay? People will kind of estimate or guesstimate or approximate, but they don't actually use the principles that the dialogue was supposed to be exhibiting. And Molly will talk about much simpler work on triangle completion that seems to show the same thing, raising the question, how do we get to Euclidean geometry? Now, why I think this is interesting, and the reason I wanted to talk about it here, is that I think the idea that language is what gets us there is a little non-starter in the case of Euclidean geometry. The nice thing about number is that when we use words like 3 and 5 in a school math class, they mean about the same thing as when we use them in our ordinary conversation. But that is not true about the basic terms of Euclidean plane geometry. What's more, when we solve arithmetic problems as adults, we tend to do it by calling on a specific natural language. We tend to talk to ourselves, and there's all kinds of evidence from cognitive tasks that language is activated when we're doing mental arithmetic, but we don't seem to solve any kind of geometry problem that way. Finally, when we ask when do kids get to natural number, the answer is around 5. But when do they get to solve even simple problems of Euclidean geometry? Not till age 10 or older, long after the heavy lifting of language learning has ended. So the question then is, what gives us these concepts? And what could we learn from the contrasting ways in which we get to these different aspects of mathematics? I won't say anything more about anything except being more than out of time. Let me turn this over to Molly.
Hi, everybody. My name is Molly Dillon, and Liz and I thought it would be really fun if I could just take it from here and tell you a little bit about geometry and perhaps the role of language in forming our conceptions in the geometric domain, and as soon as I can figure out how to do this, and how that might be a contrast with number, and how research from remote cultures might help inform our understanding of the origin of these concepts. Okay, can really only do one thing at a time. Okay, and then I thought I would also raise some more general questions that could guide the discussion afterwards. So let's see. Okay, perfect. All right. So looking out into the audience, I noticed there are quite a number of authors out there, and you might be surprised to find out that some 23 centuries later, you might still see a review of your work on Amazon or whatever the contemporary medium is at the time, such as we'll see here for Poor Euclid. And I should just preface this in saying that these two reviews, they'll be funny and entertaining, but they really get the heart of at the heart of my questions and commentary for today, which concern the intuitive nature of Euclidean reasoning, its relation to symbols and language, and how we should think about it in today's modern context. So our first reviewer claims that the propositions of Euclid or the theories here are unproven and you're not supposed to question them. This is for the brainwashed masses. So he or she states that perhaps these Euclidean intuitions are not at all intuitive at all, or perhaps they're maybe too intuitive. And this second reviewer, gives us the impression that today we might think Euclidean geometry is intuitive. In fact, we've done even better than it, but perhaps it wasn't too intuitive at some point. So for example, this book could impress the heck out of somebody that barely knows what a circle is. Or, whereas Euclid had to say things that are equal to each other are equal to one another, today we can do better. We can say in 2013, if A equals B and B equals C, then A equals C, done. Okay, again, this reviewer gives us the impression that today we think Euclidean geometry might be intuitive. In fact, we've done better at this point, but perhaps there was some point throughout human history when it wasn't quite so intuitive. And it's perhaps worthwhile to reflect on the impact of the work in its original context. So given this introduction, I just want to raise two questions today. Relating back to the question that Liz raised at the end of her talk about the format of representation in Euclidean geometry and what this might mean about its universality. So are processes of mental imagery, as opposed to language, underlying our geometric reasoning? And question number two are talking about geometric reasoning as Euclidean intuitions, something that might be really a cognitive illusion. So we'll start with our first question. Are processes of mental imagery, as opposed to language, underlying geometric reasoning? And so to address this question, or at least to introduce it, I'm going to talk about three studies very rapidly that all rely on a very similar paradigm. It's a paradigm in which participants are presented with the bottom two corners of a triangle and are asked questions about the top corner, its location, and its angle size. And this task was inspired by Euclid's Book 1, Proposition 32, which is, of course, okay, so the internal angles of a triangle sum to a constant. It's a hard thing to remember. And the idea was to figure out if participants could generate responses about the location and angle size of a triangle's top corner, given information about its bottom two corners that fall in line with this proposition. So could they generate responses that fell in line with the idea that the internal angles of a triangle should sum to a constant? And so we'll first take a look again at the Munduruku, and Liz and her group of collaborators, including Veronique Izard, took this kind of question to adults and children in the Munduruku and basically presented them with the bottom two corners of a triangle and asked them to point out the location of the third corner and generate the third angle either with their hands or with this measurement tool here, a goniometer. And the idea was to figure out over a variety of triangles whether the participants could modulate their responses such that it would capture the idea that the internal angles of a triangle sum to a constant. They could modulate the size of the angle that they generated so that the sum was equal to a constant. Of course, to Euclid, that's two right angles, but that's sort of explicit knowledge that wasn't required to complete the task. And the idea was to figure out whether or not these Munduruku participants, who have limited geometric vocabulary, certainly not specialized geometric vocabulary, and who receive no formal education in geometry, could nevertheless, again, generate these responses that fall in line with Euclid's proposition. So what I'm going to show you first are the responses from US adults. So these are Cambridge College students. And what you have on the x-axis is a stand-in for triangle size. And then I'm going to show you on the y-axis the estimated sum of the angles. And so what you should expect is a straight line, a bunch of dots, a straight line at 180 degrees, reflecting sums that capture this idea of constancy in the internal angle sum. So what we see in the US adults is pretty good. We're hovering around that horizontal line. But what the real comparison that was of interest at this point was whether or not the Munduruku would produce responses like that as well. And we see very similar shapes of the curves in these two groups. And at this point, Liz and her team concluded, okay, we have this group of participants from a remote culture who receive no formal education in geometry. And look, they have these intuitive representations of Euclid's rules. They have these intuitive Euclidean representations of how planar properties should work. Isn't that cool? And they also found that children given the same task would not be able to produce this angle constancy, this angle sum constancy. So they could say that there was something about the developmental process as humans that gave rise to these Euclidean intuitions. Their exact nature and their origins and development still left to be investigated and raised a lot of questions about what kinds of formats of representations could one use to arrive at these kinds of judgments if you aren't explicitly taught the Euclidean rules. So one thing I should also maybe point out about these findings here is that there's this slight uptick in the participants' responses. As the triangles get bigger, there do seem to be, perhaps undetectable with these data points, but perhaps there is some hint of the larger triangles giving rise to sums of internal angles that are greater than 180 degrees. So I came in at around this point, following up on this study with some of our collaborators in the applied math department, and I thought this was really cool, but I really wanted to know more about what were the underlying representations that could be driving what we were thinking of as this abstract representation. Was there any relationship between the physical stimuli properties that were being presented to the participants and their judgments, or was this a purely abstract kind of representation? The other thing was to kind of put this task in a more abstract context. So instead of saying point to and show me, you could ask people explicit questions about the properties of triangles, perhaps trying to elicit a more abstract representation. So we ran two tasks, one in which we showed participants the bottom two corners of a triangle, and instead of showing them any changes, we just said, hey, what would happen if we moved these bottom two corners out? Would the third corner get bigger, get smaller, or stay the same size? And what we could do is we could measure how participants responded to this given different kinds of transformations. So what we found is that when we told them to think about transformations that were larger versus smaller, they took more time. And they were less accurate, indicating to us that perhaps it wasn't this rule-based or language-based representation that was going into their judgments, but rather something potentially more continuous. If it was a rule, it should apply equally to when things get larger versus smaller. So we also tried to learn a little bit more about what kind of representation people might be using to perform this task by, again, just repeating the localization task. Where people would indicate where the third corner was and what size the angle was. But instead of presenting a limited range of triangles, we presented teeny tiny triangles and really huge triangles, so we could model the statistical properties of their responses. And so what we found is that the location where people would indicate the third corner was could explain how they would respond to categorical questions, explicit questions that I had raised in the first task. So we could have this predictive effect of just pointing out this visual completion strategy that was totally unrelated to explicit judgments, nevertheless has properties that if you were to put it into discrete categories would match the kinds of explicit responses that people give to geometry questions. Again, indicating that the strategy is perhaps not abstract or rule-based, but maybe is more like a mental image strategy. So the question, so that's addressing the first question. Second question for today are whether Euclidean intuitions, or really something like a cognitive illusion, are mature processes of geometric reasoning, even Euclidean intuitions, or do our intuitions about geometry reflect judgments from something like a core cognitive system of geometry that's not itself Euclidean? So if people are generating angles that are larger than they should be for triangles, is it because they're introducing curvature into their representations? That's not Euclidean. Which is to say that these representations that are guiding our responses don't have concepts that are essential to Euclidean geometry, like straight lines, infinitely small points, lines that never end. After all, we've never seen such properties in the real physical world. So the question here is, when we answer something about Euclidean geometry, are we really answering a different question, one about the properties of the physical world, as our core foundations allow us, and not about abstract entities. So in other words, if you ask someone a Euclidean question, you might not necessarily get a Euclidean answer, even if it looks like one, like it did with the Munduruku participants in the first experiment and the US participants in the first experiment, unless perhaps you're asking a geometer. That's it.
Comments, questions from the general group. What's that? Oh, no. I got it. So Liz, I have a question for you. What, like, that went by fast, all those things, but that's fine. What's your hypothesis about what's going on for the counting when kids or adults or whoever it is that is failing on the substitution? When you had that case where you have a bunch of objects, one-to-one correspondence with some things, and then you hide them, and then take one away and put a different one back. Why are they failing? Like, so, yeah.
I think they're failing because I think that everyone is interpreting the question as pertaining to the relationships between individual objects. For each of these guys, there's one of these guys. Not this set is equal in number to this other set. I think that what the tree device does in one case or the interlocking puzzle pieces does in the other case is provide a means for keeping track of larger numbers of individuals, not for representing the cardinal value of the set. That's for the kids who fail. And we'll come back to this with Julian's talk, right? Because he shows that an interesting subset of people who fail this task are people who have already mastered the counting procedure. So the counting procedure isn't sufficient for passing this task. But he also has another group of subjects who pass this task who haven't mastered the counting procedure yet. So it doesn't seem like it's necessary either. What I think is going on is the following. This is actually the slide that I cut because I was out of time. I think that if what's going on is that kids are using language to get to the concept of exact number, and specifically they're using mechanisms for expressing conjunction and also quantification, 2 5s, 2 hands, conjunction 5 and 2 on the side. If those are the mechanisms that are getting kids to the ideas that you can create larger numbers, and they will have exact cardinal values, and they will stand in 1-1 correspondence to other sets that have those same values. If they can get to that idea by language, that's not in any way going to tell them how counting works. And counting is going to be hard for kids to learn because it actually violates all of the pragmatics of natural language conversation. If you want to talk about these 7 things, why are you using words like 1 and 2 and 3 and 4 and 5? Why are you pointing to individual objects if you're talking about a property of the whole set? It seems as if kids are getting into the world of reasoning about number by using language, then they're going to be misinterpreting everything that's going on when they see other people counting. So I think that's one of the reasons why counting is hard for kids to learn. But I also think this could explain why arithmetic is hard for kids to learn, because there's nothing about semantics of natural language or about natural language rules that's going to get you to the truths of arithmetic, right? So nothing about the rules of language are going to tell you whether 2 5s and 5 2s are the same number or different numbers. And they're sure not going to tell you whether 2 5s is a bigger number or a smaller number than 3 3s, right? To learn those kinds of things, you actually need to learn the facts of arithmetic. So I think it's something that could both explain why natural number could be truly natural, but also why culture-specific procedures that use it, like arithmetic algorithms and counting rules, are hard for kids to learn. Now, I actually have a question for Molly, which is, I would have argued, I would be inclined to think that in one respect at least, the situation for geometry is the same as the situation for number. That is, I think it's entirely possible, maybe even likely, that kids who get to the triangle problems or who truly understand the Meno dialogue actually have a conceptual understanding of formal abstract geometry. What they don't have, what language doesn't give them though, is any ready means for expressing that, for applying that understanding to particular problems. Like for this triangle here, what's going to happen to it, right? And I think really that kind of understanding that you get when you go to geometry classes may be more what you use to convince yourself whether what you have simulated when you've used imagery in the studies you're talking about here has actually gotten you to the right answer or not what you use to generate the right answer in the first place. Because we don't have a system of mental representation that we can easily use that lets us generate it. Do you disagree?
I think that there are a couple of possibilities, right? You could have a mental imagery strategy guiding your geometric reasoning that could have one of two properties. It either could be Euclidean or not, or you could have a rule-based strategy or a language-based strategy that could be Euclidean or not. Right? And all of these three things could play out in different contexts. It seems like when we ask even educated individuals about the location of a third corner in a linguistic explicit context, they show responses that fall in line not only with not being rule-based, it takes them longer to do bigger versus smaller, but also not being Euclidean, insofar as they're generating locations for the third corner that are lower than they should be and that have angles that are bigger than they should be, indicating some sort of curved function, that's generating their trajectory. I think it could be very possible that intuitions that don't need to be linguistic or abstract could capture properties that are essential to Euclidean geometry, but at least in that case, the concept of a straight line doesn't seem to be embedded in the judgment. I think there's also kind of an interesting case with young kids these are data that I didn't present, but if you ask a 6-year-old a triangle completion problem where you say something like, the bottom two corners get smaller, what happens to the third corner? They say it gets smaller, which isn't compatible with a visual completion strategy either. And in fact, what seems to be happening there, we might hypothesize, is that they're using a linguistic rule, but it's a bad one, and it's not a Euclidean geometric rule either. So I think my intuition is actually that that there may not be these abstract intuitions about that capture all the properties of Euclidean geometry. We may come really close, and it may provide a medium on which to map the formal rules, maybe in the context of proving it to yourself or learning it in school. But there's this noise aspect that seems to lead us astray when it comes to perfectly straight lines and infinitely small points.
I think this is just a quick follow-up on these points, because I'm thinking, I don't have to research these topics, but I have to teach them to undergraduates every year. So I'm always trying to figure out where we are with these debates. And you presented a couple of options about natural number and what different theories might predict. But I'm finding myself listening to all these talks wondering about a fourth option, which is that there isn't an abstract concept of natural number or geometry. What there's knowledge that gets increasingly elaborated, and like tool use in other ways, we learn to use these tools in more sophisticated ways for different tasks. And sometimes we can use them for one-to-one correspondence, and sometimes we can use them for compositionality. Sometimes we can use them to estimate triangles in some contexts, but not others. And that what you have are clearly some innate evolutionarily conserved core representations, and then increasingly sophisticated tool use, which you can apply to some tasks and not others. So I'm wondering what you think of that.
Yeah, I mean, I think you're right. I think that's a possibility. I think it actually brings out really nicely the potential contribution of research in remote societies. So one of the problems with running more studies in Cambridge is everybody's kind of got access to the same tools. So it becomes hard to distinguish these things. But if you can go to another culture where they don't have a counting routine at all, or where they have a language that doesn't compose numbers in the same way that our familiar languages do. It doesn't have a word for and, as Dan was saying for the Pitahan. There's a real possibility there for distinguishing these views. And to me, that's more interesting than actually trying to make bets at this point, which is going to be the right one. Yeah.
This is just maybe a dumb question about the experiment. Did you ever try with the triangles upside down or sideways?
Yes, we tried them sideways. And
what
so we did with the statistical experiment where we had the people produce a corner that was too low, we rotated it 90 degrees, and there was the same compression towards the base of the triangle. Yeah.
Okay, thank you very much. I'm going to give you these things. These are on the warning signs. Okay? Okay. Okay, the next speaker in the workshop is Julian Hara Ettinger, or Julian. Of relevance to the workshop, Julian has collaborated with me and Steve Piantadosi down in the Chimani on number knowledge. I got to know Julian when he was a grad student in BCS in our department here at MIT over the past 5 years. And he first came down with me and Steve to work with the Chimani in 2012, I think. And he has led many projects on the topic of number knowledge, which he's going to be talking about here. Julian has a second research program in collaboration with Laura Schultz, who was just asking a question, and Josh Tenenbaum, which is working on the naive utility calculus, which is interpreting people's actions as trying to maximize utility in terms of performing an action versus the cost of the action. So he uses this framework to explain complex cognitive phenomena, including pragmatic reasoning in language and rich social interactions like, am I going to help you or not? And so Julian's actually starting at Yale in the fall as assistant professor. Julian.
Thank you for that introduction. Thank you to the organizers for putting this together. And I also want to start by thanking the people that I've been working with. So the work I'm going to talk
with some observations from language acquisition, because I think it gives us some perspective into some of the many hard things that children master actually quite easily. So we know that infants are able to fast map nouns from complex scenes. We know that toddlers are bootstrapping verbs from fleeting events. We know that children are able to disentangle the meanings of quantifiers like some and most and many from what speakers' intended meanings are. So from that perspective, number words are really strange creatures. So as many of the prior speakers have mentioned, toddlers are producing them as a whole set in this count list. And despite the fact that they don't actually know the exact meanings of these numbers, words, right? And that on its own is really kind of puzzling, because usually in language acquisition, you get this very robust pattern of comprehension leading production. So children are producing them, but they don't quite know what they mean. And they're incrementally mapping them onto exact sets over the course of the next couple of years. And it's not until the school-aged years where children are finally converging on something like a full-blown integer representation, something with the representational capacity to understand cardinal principles, principles of numerical equality, successor function. Now, this raises the obvious question of why is it that number words are so hard to learn? And a lot of the prior speakers have focused on this vast gap between the initial states, like what infants start out with in terms of object files, analog magnitude, and the end state, that of integer representation. But I really want to focus on this notion that these old theories that children have about what number words mean, they're really sticky, they're really persistent, and I think that that's what Julian's data really highlight. And so rather than a single inductive leap that gives children all of this integer representation, it seems like children are juggling multiple possible theories that really persist throughout development. Okay, so let's think a little bit about why is it that these old theories, these non-integer theories of number, why is it that they are so hard to replace over the course of these multiple years of development? And I think that the first reason why they stick around so much is that they're the lens by which children understand their current evidence of the world, right? So children are producing them, they seem like they understand what they mean. And so if you have a hammer, everything is a nail, right? And in this case, it seems like the hammer is this object representation. I think the most kind of exciting part of Julian's data was the data that he showed where full counters, despite the fact that they can figure out how the count list enumerates exact sets, retain this notion of sets as having object-like qualities, right? So when one cookie is replaced with another, clearly we as adults know that it's the same set, but children often say that they're different, even if they're succeeding on the give-end task. This is different than what they're doing in the identity cases, right? Where they realize that, in fact, in the identity case, this is the same set, very similar to performance with the subset knowers. Veronique's data. And all of this is really strange from the adult perspective, except when you think about what the child is thinking when they're at this stage, right? And in particular, if the child thinks that sets are simply these objects with complex individual parts, then when you're asked a question like, hey, this car, is it the same car when you replace a tire on it, right? It feels a little weird to say that it's identical to the same car, right? Because it's slightly different, right? Or I guess an even kind of more obvious example is if you take a face like Mr. Potato Head, would it be the same face if you replaced his nose, right? And maybe it feels kind of weird to say it's the same thing, right? It feels slightly different. And so, all this to say, theories are powerful because they shape the way in which we take in the world. And so children may hang on to this notion of sets as objects because they're inclined to construe these sets as having individuals within an object, different parts within an object. And so this leads to this illusion of understanding how numbers work. These illusions are not unlike the kinds of illusions that we as adults often walk around with when we think about how we know the world works. And that's a point that I want to come back to in a couple slides. I also want to mention that these dynamics are quite similar to the kinds of default interpretations that we as adults use, right? So by virtue of the fact that we are wonderful readers, it becomes harder to really attend to just the ink color in an incongruent Strube task, right? Or in the world of sentence processing, the linguistic biases that we use to understand sentences of real time incrementally, those often create some difficulties in understanding these garden path sentences, right? And I'll note that in both these cases, these are instances where it's been noted that children have a lot of difficulty tamping down their initial interpretations. And so one possibility is that this inadequate domain-specific knowledge of numbers is hitting up against these domain general dynamics of inhibiting dominant interpretations. Okay. So a second reason why old theories persist may be that the numbers themselves are kind of learned, our understanding of integers are created in a piecemeal process. And so typically people talk about this in the context of one knowers, two knowers, three knowers. And this is interesting, right? Because it suggests that you can't across these different cultures, you can't bypass these different stages in order to get to the end. And it's very similar to the kinds of phenomena that we know very well in language acquisition, right? You have to learn single words before you can learn to combine them. Knowing some nouns helps you acquire the meanings of verbs. Importantly, I don't think that we know quite as much about what the theory the child has at these individual stages, right? We know what characterizes these behaviors, like how we're going to diagnose that you're a two-knower, but it's a little less clear what they're walking around in their heads thinking about how numbers work at these stages. And in particular, Julian's data suggests that complete knowledge of integers doesn't even come in all at once. Children who understand there are children who understand the principles of exact quality but aren't full counters, and there are full counters who don't understand the principles of exact equality. And so I guess all this to say, mastering counting doesn't guarantee integers, and this isn't that surprising when we can consider the properties of intuitive theories that we have as adults, right? There's the really classic studies that show that college students who understand or who can memorize the equations of physics have very little knowledge of how objects move in the world, making predictions about how objects move. Similarly, I begin my semesters asking my college students why do we have seasons in the world, right? And so they can tell me that there are 4 seasons, they can tell me that the Earth goes around the sun, but they can't tell me exactly why there's this relationship between seasons and climates, why they assume that it's because the Earth is at different distances away from the sun, but don't realize that, it's like kind of awful every year when I do this, but they don't realize that, some parts of the Earth only have 1 season, and there are different seasons across hemispheres. And yet they experience 20 plus years of seasons, and so this is, they have this intuitive understanding that they know what's going on, and they stick with it. Right? And so all this to say that Julian's data, I think, provide this notion of how is it that children might potentially overthrow these old theories, right? And so we saw that every every child in every culture has to go through these stages, but across cultures, they're moving through these stages at different rates, right? And so this might reflect the kind of cultural norms, expectations that you have about how much number do you need to know, right? But within a culture, Julian's data showed that age and schooling on its own aren't necessarily great predictors of whether children understand exact equality. Instead, it's their knowledge of counting that ends up being highly predicted. Now, this is consistent with what people have said for a long time about how counting might play a role in converging on integer representations. But I think that it's even if it's not a necessary tool, it's certainly an effective one, right? And in particular, it's effective because it uniquely allows a child to provide her own evidence rather than waiting for other people to label the sets for her, right? Because the labeling of other people's labeling can be highly ambiguous, but when you generate that evidence for yourself, you can it really hones your attention on ways in which there might be conflicting evidence out there. Right? So you might imagine that a child who initially thought that substitution leads to different sets can then take a pause, count it out, and realize that it's the same number word. And that might be the critical piece of evidence to really kind of hone in on these exact representations. All right.
I don't know if I have that much to say other than I vigorously agree with all of this. I'm kind of jealous in the nice way in how nicely the analogy with physics works. I think that's exactly, I love how to thinking about it that way, where most physics students first learn a bunch of equations, and then from those they start to derive the intuitions about how physics works. But it can't be that all college students, all humans do that, because then you have the problem, how did we come up with these equations in the first place? So occasionally, we need some people who can come up with new intuitions and then build those. So it seems like it's a nice way to think about number, where it's probably that many children learn these algorithms, and then from those they start extracting knowledge. But there has to be someone who first can realize these properties, and then has to notice these properties and then realize that you can build an algorithm to try to extract this information precisely. So thank you for that discussion. Does anyone have any questions? Yeah?
Yeah, I think I was really, I'm sorry. I was really interested in what you said about how counting can provide evidence, but I think there's an interesting additional possible way that kids can get evidence about exact equality, which is by using their smaller number words, right? So if you have a set of 5, and now you add 1, and you see beforehand that, look, this set here is 3 and 2, but I add 1 and now it's 3 and 3. It's no longer 3 and 2. That actually this provides a way that kids can give themselves evidence, and it could explain Julian's data for why it is that although counting is neither necessary or sufficient, the number of number words that the kids have, small number words that they have, is highly predictive. And Barbara has data that's shown related things with US kids. It could be because they're able to use set composition plus the evidence from the small number words to actually learn about the properties of the larger sets.
Yeah, I mean, I guess I completely agree with you, and I think like another thing that I was thinking of that didn't make it on the slide is kind of thinking about kind of the intuitions that, so a lot of the themes I was kind of trying to draw is like how, you compare adults and kids look so dumb, but I mean, the reality is that adults aren't necessarily that smart either sometimes, right? And so thinking about ways in which like adult intuitions about large numbers kind of break down pretty quickly. And so kind of ways in which there might be frequency effects that are occurring in the developmental stages where, having frequent numbers or having numbers that you're very frequent and comfortable with allows you to have better intuitions about how they work. Yeah.
So I'd like to ask about intuitions about Mr. Potato Head. Yeah. So I just thought that was a really interesting point. Except for me, it was the same face in the same car. And I'm just wondering whether anyone, yourself or anybody else, has looked at individual variation in those kinds of judgments and whether that in turn predicts the kinds of set-based behaviors that you're seeing in the children in these kinds of cases.
I don't know of any work that has done that. Very interesting.
So I also, is this on? Okay, there we go. So I also really liked the analogy to physics and the discovery of formal rules and patterns. And I wondered how useful it would be to push into sort of more, let's call it more advanced aspects of counting, right? That where we actually have historical or when counting was discovered is lost to time. Other things are more recent that still involve some of the same things we talk about. Like I was struck when Liz was talking about one-to-one correspondence, I remembered, wait a second, one-to-one correspondence is how we prove that there are two levels of infinity, right? There's countably infinite and uncountably infinite. I personally have no intuitions about either of these, even though I've gone through the proof several times. I actually looked up in Wikipedia because I could not remember if rational numbers were uncountably infinite. They are not. They are countably infinite, which blows my mind. It seems like they should be uncountably infinite. But they're not. But the proof's actually very straightforward, and it just requires understanding one-to-one correspondence. And yet apparently it was, a couple millennia between like people discovering irrational numbers and discovering this proof. And so this makes me wonder whether there's any headway to be made here in sort of teasing apart the, having this information and being able to deploy this information to actually then, understand something about the world or about number.
Yeah, I guess the analogy to development, there is this sense in which, there's a sense in which accounting is a little bit like, it's like a microscope or a telescope that allows the child to observe processes that might have previously just kind of flown over them, right? And so I think, in that sense, having this technology, this kind of cultural invention allows you to kind of, there's both the understanding of it, and then once you understand it, you're in a position to kind of move forward.
Yeah, and I'll also add, like in the case of something like number or physics, another thing that's interesting about it is that, yeah, in the case of proving different infinities, the first way you do it is by showing that it actually falls out of this, the diagonal argument thingy of how you can never fit into the natural numbers into the real numbers. But once you know that, having that knowledge doesn't mean that you have to always derive it that way. And I think one of the things that I really like in math is how people just spend a lot of time trying to think about analogies in which they can come to get a child to understand. And I think in the case, I'm not even going to try because I'm going to get it wrong, but there's a way to teach children that there are different sizes of infinite, and you just do it by doing this guessing game where you tell them every day, I think that cover story something like, you're in hell and you get to go to heaven when you guess the number that the devil is thinking about. And now the question is, what strategy do you adopt? And if they're thinking of an integer, you know that you can just start from 1, 2, 3, and you're eventually going to get out. And I forget, but the point is, that I think that there's a lot of sophisticated knowledge that we get out of cultural tools, but once we have it, we can kind of reconstruct it in a way that then becomes something that feels very intuitive to the next generations, and we keep building up.
Thank you for two fascinating talks. Julian, I was thinking about your example of the bag of rice and the idea that there's an exact number of grains of rice in there. Mm-hmm. And it seemed to me like if we actually tried to count the grains of rice, we would very quickly run into some problems because some grains of rice would be broken and we wouldn't know exactly which ones to count as whole grains or not. We'd be like in a whole 2000 recount election situation where lots of broken chads and so on. Hanging chads, I apologize. And so I'm wondering if learning to count and learning the math systems that we have developed culturally actually creates this illusion of exactness, that there is exactness beyond what actually exists in the natural world. That you can say to a room full of very smart people, of course you know there's an exact number of grains of rice in this bag, and most people say, yeah, okay, because we believe that's likely to be true, when in fact the world is messy, and when you try to count very large numbers of any natural thing, you run into lots of problems. So is there a flip side to learning mathematics in that it kind of essentializes number and exactness?
Mm-hmm. Yeah, I love that idea. I hadn't thought about it quite that way, but the reason I like to use the rice example is because when I started working on this, I found it so counterintuitive that someone would not know that, think about it, set exactness as being a core property. I was like, how could children not understand this? And when I think about things like bags of rice, I lose the intuition a little bit, and I get a little kind of saying, I guess technically yes, but it feels a little blurry. Yeah, so I love the way you put it. I think it is possible. Yeah, it's interesting. I guess the way I would like to think about it is as learning some kind of noise function where, if I ask you how many grains of rice are there, you could technically answer. And if you said, well, I don't actually, if you refuse to count, you said, what if like there are these little pieces? I feel like we would engage in this kind of interaction where I would say like, well, you know what I mean. So it does feel like learning to count might also, another way of putting it is, yeah, the algorithm constrains like the space of meanings that of what we can mean when we ask how many are there. Yeah, thank you for that. Bevel?
Yeah, so this has been a really fascinating day for me. I feel like I'm a tourist here in someone else's continent because it's not really my field. But following in the footsteps of Josh McDermott, whose one piece of data is his children, the thing that strikes me about watching my children learn to count is the importance of touching. And they're decoupled, the touching action is decoupled from the learning of the word, the number word. And it seems like the critical ingredient was the step they made when the word got yoked to the act of touching. What made me think of it was when you were talking about your own personal evidence, acquiring your own evidence. It was in this moment when they were like, oh, this thing maps to this thing, and since touch is a discrete entity, it enabled them to then build out in this idea of oneness, that this is one touch and this is another touch, that it becomes embodied. And in that way, I sort of think of the whole problem as much more, how is the kid relating to this thing as it's useful to their own experience of the world? And then the bag of rice becomes, well, you're not going to sit there and touch every thing of rice. You might carry the whole bag of rice, in which case, one kernel or not, it's kind of Weber function. It's like, it doesn't really make any difference. And so you then are stitching on two kind of embodied principles. One is how much weight you can carry, which is a sort of other thing from this pointing thing, and maybe you're asking these kids to do both those things when you take a bag of rice and remove one and put it on. So I'm just wondering, because it seems like none of the work on counting or number that we've heard about actually connects to the way at least my naive experience of my children and others' children's counting actually does get developed.
Yeah. Thank you for that. I'll add, I don't know if any work that's been done on that, but I think it's super interesting because I have a conflicting intuition, which is, I agree, I think touching might let you do the mapping. I like that story a lot. But I think in that case, it might even push you further to just learning some kind of game without really understanding the meaning. So you learn like, oh, when I'm doing this, I just loop through my list and I touch each thing, and then I'm done. And it feels like a big achievement of counting is also knowing that you don't necessarily need to do that. Like I can count how many times I was sad the last month, or like you can combine sounds and lights and other things. So I think we don't know, but I think it's a super interesting question asking both what role does that play, and if it plays a role, then how do you actually detach the meaning of counting from it? Is there anything you want to add?
Yeah, I mean, I have a young child at home, and I have the experience where she, it's weird because I study number, and I could see her just going like this all over the place. I guess I will add, as you said, that children, the funny thing about being a subset knower is that you're both quantifying sets like objects, but also sounds too, right? So like a two knower in objects is also a two knower for counting beeps and actions too, right? And so there is a sense in which it's an amodal representation. Yeah.
Yeah. So there's always a question. We have maybe one more. Is that fine?
Is this on? Yeah, it's on. I was going to confess, as a number researcher, speaking of how kids really in the real world learn numbers, there's like a dirty secret that none of us admit, which is that they actually learn the word two before they learn the word one. But that you only see that if you do natural language observations. So what happens is toddlers will say like bus, and then one day you're driving and there are like 2 or 3 buses and they say bus, two, right? And so it actually looks, if you look at natural usage, like a kind of a a word that means like duplication of something. So when there's shoes or buses and it's not limited to just two, it's like there could be three, there could be five, but they say two sort of as a plurality marker or as a multiplicity marker, but when we get them in the lab, if that's all they know, they look like pre-number knowers, right? They don't distinguish one. So I guess what I'm trying to say is the word one isn't just like you've identified an individual, it's that you've identified there's this dimension of numerosity and it's upper bounded. So you're saying one, not two. And Dave Barner has a study which annoyed the hell out of me when it came out, because I said a long time ago, like 11 years ago or 15 years ago, that the word one was learned like the indefinite article. So to say one bus was equivalent to saying a bus. And in fact, it is the indefinite article in languages like French, right? And then Dave turned around and did a study where they put a banana on a plate and said to kids, is there a banana? They put 2 bananas on a plate and said to kids, is there a banana on this plate? And kids said yes. And they said, is there 1 banana on this plate? And the kids said no. And so I think we aren't quite sure. Like in real life, it's like there's individuals and then there's individuals replicated, and we start using number words to
I don't even know if it's a real thing. So you're talking about the traces in, like the hypothesis that there are empty categories in intermediate clause boundaries. Yeah. I'm not wild about our experiments there. I think our experiments are p-hacked. And so.
Really? Because I basically replicated it. And stuff kind of also replicated it. Yeah. And I got the same results.
Oh, you had the same materials?
Yeah, same materials.
Okay, well, that's good. That's a good sign.
Yeah, well, that's what that was.
Well, I stopped working. Yeah, no, well, I like to see.
I don't know what the fluid work goes. I tried doing it in the EEG group, and it's not clear what to really look for there.
Well, maybe we should talk about that. I can't do that right now, though.
Okay, no, that's fine.
Okay. Hey.
I'm a little hypoglycemic at the moment. I am, seriously. I'm gonna need to eat something. Is there really a piece of cake out there for me?
Yes. No, absolutely. Yeah, it's fancy too. It's from that fancy. No, it's coming here. Bring it here. It's good to be there. No, I just.
Oh boy.
I'm trying to do my best. I don't think it's got much to do with language, but how do I get this to show up, do you suppose? Do you know how I get that to show up there?
Well, you don't have a Mac.
Do I have to do this function F7?
It's probably something either over there on the screen.
So, you want to stick with HDMI and use this dongle through here?
I don't care.
Just look a lot better.
Sure.
Really.
I'll do whatever I'm told.
We should just make the other one much less visible. Make this very visible.
Well, that wasn't clear to me that I even had this option.
Okay.
And now it's going to show up there? Oh my God, but that's the wrong thing. How do I make it so that it's not that? because that's just duplicating what's here.
What do you need it to look like?
Oh, hang on a minute, let me see. What? Let me see. Okay. So if I have this, and I put it in there, then it should just show the presenter mode. It should be.
You want presenter mode here?
Yeah, exactly. So what do? I go.
So we're in PowerPoint. Let's
Oh.
see, go to
Settings.
slideshow.
And
use
use presenter mode, and then I have to go. It's control. Control panel. And then it's
let's see. This is a Mac
So I
user.
want display, landscape, and I want
Identity. Is that under identity? What you want? Oh, I see. That's. You want to make it. You want to extend the desktop, right?
Yeah.
That's presenter view right there.
No, this isn't. This is what presenter view looks like. But you see
Right,
that,
so
and
now
then
you need to
do that. And now I don't have presenter view here, you see.
Oh, let's see. So, what if you went to toggle that switch off? Just see what that does.
This doesn't usually fail. That's what's weird. I think that's what I needed to do. Keep changes. And now. Oh, but that.
Good?
No, now it's.
What are we looking at now?
Now it's just showing my one slide. Well, it's not presenter mode, but whatever.
Oh, now you can use. Do you want to go back to VGA?
No, we'll see what this does in the end. There we are. All right, I think this is going to work. No, I think there we are. Yep. Okay, good.
or anything like
There's this
tricky?
HDMI thing, so if you've got a regular VGA, you use
Oh.
that instead, apparently. But my issue was more just that.
So theirs is, they don't have VGA, they've only got HDMI.
No, they do have a VGA if you want it, but he says it looks really shitty, so that's why
I see.
that was what caused a little moment.
Okay, I think I have HDMI. Hey. Okay, so one or the other will work for sure.
Look who.
Look what he found.
Showed up. I've never. Well, it's funny because I play this game at SFN every year, the Society for Neurosciences, where I mean, it's gotten to the point where I know enough people that it doesn't work so well.
So we're good.
But so I was looking around the room going, which one do I think is Terry right here?
So you guys saying you don't want to use HDMI for one of them?
I think I'm fine.
Okay.
That's HDMI. So we should be, I've never tried it before, but
First time for everything, but all right.
Good. If anything, if fire breaks out, we call you?
Absolutely.
All right. Great. Terrific. Thanks.
But I will have an extra ice cream. Because they're totally coming out. They're already melted. And ice cream is the quickest way to get the sugar.
So these are the leftovers from lunch?
No,
Yeah.
leftovers. This is what we were deprived of.
Oh, this is what you went there for, huh?
Yeah, I know. And then he's like, no, you can't have dessert. And I was, you know what I love? I love that. That's what I love. Look, I love that. That's the garnish. They decided that we needed a garnish. Because you got a box. You should have one. I'm not going to get
already passed.
Oh, no. Very kind. We also keep eating ice cream. They're like, why? Nobody else is gonna have it. So it's one or the other?
Yes. This is you? Oh, so you switched?
Don't touch anything.
How did you switch from?
Because they told me to.
I see, that's for the, oh, that's me.
Yeah.
I'm gonna warn you these times.
Oh, good.
And you can just talk while you want.
I know, I was just like, I was like lately discovered that was what I learned.
I would do it at the conference. I would definitely stop people at the conference.
I'm not famous enough to be thought it was. I thought it was a live stream thing, and it decided to take the videos off. I was planning them somewhere in like 2 months. I do too, but you do. I think you do need to tell people that the talk is tomorrow.
Well, I think for the conference, it's not a problem. It's just for this workshop, it's an issue. For the workshop, it's an issue because it's like, this is like just invited to talk about, you're invited to talk about.
And unpublished stuff.
Yeah, but the conference, that's work that needs to be done. So, like, say, you don't want to. But the workshops, I think,
Yeah, I would like the talk to be disseminated. Actually, I thought that I would like to request the talk to be disseminated. I don't mind if it's broadcast now, where people can tune in live. That's different. Maybe the show out there and asking questions.
What do you guys, is there a piece of your class?
It's broader context. Yeah, we'll see. You said that you didn't used to hear what I was going to say, so you can be like, that's not what I said. That's not. You're fired. Well, the latest thing that's happened to me is that someone posted what they were going to talk about at this Harvard Systems Club that I used to help run, and I got the announcement, and it was just like, no one has ever shown X, and I was like, we did in this 2013 paper. So I wrote to the guy, and I was like, we showed that in 2013, and then they get this email, you've been removed from the listserv.
You get removed from it?
This is like
It kind of is. Well, I kind of don't really care, but it was funny. I was like, oh, by the way, it's 4:52, which is now.
No, but we said always at 4:50?
Yeah.
And then it should be 4:55, actually, because again, the captioner was not happening.
introducing me.
Yes.
Oh, you are? All right. I hope everybody claps.
Oh, yeah.
There seems to be a great variability of where we get applause. I've been marking it. In fact, the last I'm now going to make one clap, and then everybody claps.
Okay.
4:56.
I see that. It's right there.
So
See that
Liz
there?
spelled tea time.
No.
Liz spelled tea time.
Please don't. Please don't do that.
Yes, I see that. I'm going to wrap up 15 minutes later.
Yeah. Hey, historically. Okay, I think we're going to start. The next speaker in this series is Bevel Conway of NIH. Following his undergrad at McGill, Bevel's Canadian, Bevel went to Harvard and got his PhD there, and then following his PhD, he was a member of the Harvard Society of Fellows for 2 years. Soon after that, he got a faculty position at Wellesley, where he was for many years, until he moved to NIH this past year in Washington. He's a world leader in how color knowledge is implemented in the brain. Towards that end, he works with monkeys trying to discern what brain networks do what in the perception of color. Bevel and I met about 3 years ago, I think it's 3 or 4 years ago, when he came to MIT from Wellesley to give a talk. I mentioned in passing that the Chimani have vary hugely in their use of color words to describe colors. He found this fascinating and pointed out this was not common knowledge in the way that researchers on color language talk about color words. So consequently, he got me a light box, and he set up some lovely materials from the Munsell color card set, and I set out to run color labeling tasks in Chimani, and he's going to tell us about work from that project here. I want to mention one final an anecdote about Bevel is that his name is a non-word, Bevel, and if you type in your spell checker, it'll return evil an awful lot of the time.
And yet he still wanted to collaborate with me. All right. Thank you so much for the chance to speak to you today. As Ted alluded, my background is in visual neurophysiology, and my lab is especially interested in color as a model system to understand how peripheral signals from out there get turned by the brain into thoughts that can ultimately drive action. So color is also interesting because over the course of history, humans have invented many new pigments. They've actually changed the natural environment that they expose themselves to. And so comparisons across Western and non-Western cultures could provide important insight into the broader set of problems about how brains and minds adapt to new pressures. So I was very excited when Ted approached me and said, hey, these Chimani people, they do something peculiar with color, I think. Are you interested? I was like, ooh, that sounds very interesting. Now, many people have contributed to the work that Ted and I did. Of course, Ted, who led the team to collect most of the data, all of the data, and his team of Richard, Julian, Kyle, Leon, Mitchell, and Steve, together with my postdoc, Siva, these people have been crucial in collecting and analyzing all the data and figures I'll present. It's been a joy working with these guys, and I've learned an enormous amount. Okay, so a central problem of human cognition is how we transform continuous variables into discrete categories that are instructive for guiding behavior. And in the case of color, the question is, how does the brain turn wavelength, continuous variable, into these color categories? The problem's a very old one. Hundreds of color ordering systems have been described, and there is still no consensus on what the right color ordering system should be. In their book on the topic, CUNY and Schwartz remind us how often our unfounded prejudices have filled in inconvenient gaps in knowledge. My favorite example of this is Isaac Newton, who insisted that there must be 7 basic color categories because there's 7 elementary notes in the Western musical scale. And for Newton, color and music were bound by the same universal rules. Isn't that obvious? This notion seems absurd today, and in fact there's no evidence at all that music and color are defined across all cultures by 7 categories, or even what the fundamental rules are for music or color. Okay, so our empirical understanding of the organization of color was really transformed by the work of James Clerk Maxwell, who in the 19th century showed that you could match any color by mixing in various proportions 3 independent primaries. A lot of people translate this into their 3 primary colors. What they don't realize, and in fact I didn't know this until I started doing this work, is that it doesn't matter what 3 primaries you use so long as they're independent. The 3 that I have illustrated here just happen to be ones that are readily available when you pass electricity through certain gases. So for every wavelength, every color in the world, we can then plot the relative proportion of any primaries, and the convention has been adopted for these 3. If you normalize the output of the 3 primaries, then you only need 2 numbers to describe every color, and from that you can then plot all colors in a color diagram. And the convention was adopted by the Commission Internationale de l'Éclairage in 1931, where they came up with this diagram. The black arc in the middle is the black-body radiation curve, the daylight locus, we sometimes call it. And around the perimeter, you can trace out wavelengths, starting with long wavelengths, and then you can follow all the way around through middle wavelengths to the full rainbow. The horseshoe arc is connected at the bottom by the extra spectral colors, the purples, which Stephen Fry calls pigments of the imagination. I like that. So this space has a nice grounding in empirical science, but no matter how you might conceive of it, it really doesn't look like it's uniform in any sense of the word. Like there's much too space allocated for green. Well, an entirely different tradition was adopted by Albert Munsell, who Ted alluded to. He was an artist working in the late 1800s, early 1900s. In fact, he had an affiliation with MIT. And he set out with the assumption that colors could be defined by 3 fundamental variables. Again, you know, we have to put this in quotes. This was his prejudice. We still don't really understand what the basis is for these variables, but nonetheless, it's been an enormously useful system in industry. So the amount of lightness, or black and white, he represented along the vertical axis, the amount of colorfulness, that saturation along these spokes coming out from the vertical axis, and then hue forms a circle that orbits around the vertical axis, and you can see the complete space with this little inset. Now, one difficulty with creating a physical color space is the limitation imposed by available materials, in Munsell's case, pigments. In prehistoric times, there were basically only blacks and reds, so that would allow for the representation of a very small gamut in color space. And all printed chips, including the Munsell chips, have a gamut like the CMYK triangle shown here, which is also only a fraction of the color space. Despite these limitations, printed Munsell chips have become the standard for studying color categorization, especially in non-Western languages. And the most extensive study of color, which Terry Regier here has worked very heavily with this data set, is the World Color Survey, launched by Berlin and Kay. It's an incredibly impressive study that undertaking that cataloged color naming in about 110 languages in mostly non-Westernized parts of the world. So the large scale of the survey would seem to suggest that the issue of how languages categorize colors is now settled, but unfortunately it isn't. The question continues to be caught in this crossfire between universalist claims and cultural relativism. So on the one hand, languages that have a sufficient number of color terms. It's been well documented that languages vary in the number of consensus color terms that they have. But if you have a sufficient number of them, then the color terms tend to be assigned in predictable ways to the color space. And I credit Regier et al. For lifting this figure in which they summarize 4 example languages. On the other hand, there's well-documented variability in color category boundaries among languages, which together with lack of any knowledge about what the forces are that are actually driving these fundamental categories has really propelled this notion that the categories reflect something about culture. In particular, relativists have harped on a methodological issue with the World Color Survey, and it's an important one that I should spend a second or two to flesh out. So the survey was carried out by dozens of independent teams scattered around the world who were tasked with a rather complicated, implementing a rather complicated set of instructions. In some remote cultures that many, in fact, as I learned from reading Levinson's work, lack a superordinate word for color. So asking the question, what color do you see, is kind of meaningless in their culture. You can sort of imagine 2 extreme ways in which investigators would resolve this problem. On the one hand, they might bring with them their own prejudices about what terms people should use, or they might just sort of sample and then create a kind of limited set of things that they think make sense, and then require that participants use something that makes sense, that's in that limited set. Alternatively, you might imagine a more free-form kind of paradigm where people are basically allowed to say whatever they want. So it's not known how this variability in implementation has confounded the data of the World Color Survey. We don't know if it has. The data are incredibly valuable. But it's not totally nuts to imagine that Western investigators have somehow prejudiced people into saying certain things that maybe they otherwise wouldn't have said. And you know, we just don't know. So when Ted approached me, that was actually the first question that I really wanted to know, was can we have in the wild just information about how people talk about color terms, about the stuff in their world. And importantly, we needed enough data from enough participants that you could do some sort of statistical analysis. So Ted and his team, we hooked them up with a car battery and a light box and some Munsell chips, and they set off up into the Amazon to go and ask participants to name colored chips. And they performed 2 different versions of the task in 2 separate populations, 2 separate groups of people. The tests were conducted about a year apart, so these are different people doing the task. But one version was a fixed version of the task that was done after the free version of the test. The free version of the test, simply, what color do you see? Just a little light card. That's the only information that you're given, is the card on the light box, and then they just tallied up all of the words that people used. And then they collected the modal terms that people used and went back and did a fixed version of the task using the most frequently reported terms. And here are the results from the free option task. The color of the diamonds reflects the modal color that was used, and the size of the diamonds reflects the number of people that reported that color term. So you can see right away the Chimani diamonds are a lot smaller, except for red, which shows this variability that Ted described just interacting with the people. But the modal terms themselves do recover some similar structure in terms of the color space. They carve up the color space in a way that's very similar to English and Bolivian Spanish, providing some empirical evidence for this universalist claim. Okay, so we'll compare this to the fixed task in a minute, but to do so, we wanted to apply an information theoretic approach, and here I've lifted another slide from Regier et al. This is also an analysis not unlike that used by Lindsay and colleagues. You can think of this analysis as a kind of communication game. If I've got a color chip over here and I'm looking at it and I use a color word to describe that chip, how many guesses does it take you to home in on exactly the chip that I'm talking about? And you can formalize it with this equation in which we're simply trying to estimate the surprisal value of a given color chip given all of the words that are used in the population. Now, what's unique about the way we've deployed this analysis is that we do this on a per-chip basis. So we could also do what others have done, Regier and colleagues have done, which is look at the average surprisal across all of the chips and come up with an estimate of the overall variability in the language. But we're interested just in this chip analysis to begin with. So just to, as a starting point to compare across the languages, we made two discoveries. So if you look at the average surprisal across the languages using the fixed or the open task in the three languages we studied, it turns out the communicative efficiency, that surprisal measure on the y-axis, doesn't really change, which was an enormous relief to me because that means that the World Color Survey data are actually quite valuable. At least in applying an information theoretic analysis. Now, the number of color words used obviously does change. That's not surprising. We've constrained them to use a smaller set of color terms. But this means that we can now deploy the same analysis to all the World Color Survey data. And there, what that means is that this variability that we see in the y-axis is actually meaningful. This is probably a fairly accurate representation of the variability in communicative efficiency across languages in the world. So the second discovery we made was that per chip, the average surprisal across the different languages actually had some systematic pattern. So you can see here the average surprisal is in the gray value, black is lower surprisal, and light is higher surprisal. Although the Chimani show on average higher surprisal, the gray values are all higher, overall there's a trend. And we can actually rank order the color chips by their surprisal, and you get a DC offset, so the overall average communicative efficiency is lower for the Chimani, but the rank ordering of those color chips is about the same. In fact, it's highly significant. And this pattern isn't explained by the unique hues, and we can get into all the gory details of other theories of conoponency that people might have advanced to explain it. The question is, how generalizable then is it across languages? This is a lovely plot that Richard made, in which all of the languages of the World Color Survey are now ranked according to their average surprisal. You can see there's lots of variability along the x-axis, but within each language, you can normalize them, and you get a rather striking pattern of a fundamental, universal categorization of what we would call warmer colors communicated more efficiently than cooler colors. And although warm and cool are not part of the canonical set of basic color terms, they are widely recognized in culture and in painting and so on, which was my original background. So I was really struck by this pattern. And in fact, this communicative efficiency estimate provides what I think is the first actual real empirical answer for why we have this categorical distinction between warm and cool. It is a distinction that reflects the fact that we communicate warm colors more effectively than cool colors. So that's very satisfying, but you might ask, why do we do that? And to that, well, I should also mention, it may also explain something about the bulges that you see in the Munsell space, where the orange and warm colors are displaced, are allocated more space in the space. So, but why is this the case? Well, to answer that question, we did an analysis of natural scenes. Now, it's been shown in many, many studies that the chromatic statistics of the natural world are biased towards orange and blue colors. So those are the colors of the daylight axis, these warm colors. We've shown and others have shown that this is also reflected in the statistics of the neural representation. It's also the explanation for the dress, if you're interested. But no one has done an analysis of natural scene statistics filtered by what humans call objects. So we did that, taking advantage of this large database that Microsoft has produced. in which they had interns go through hundreds of thousands of photographs and determine whether or not they had a salient object. They then put bounding boxes around them, and then people in my lab went through each photograph that had an object and decided whether it was the pixels were part of the object or not part of the object, and whether or not they were naturally colored or artificially colored. And then we did a very simple analysis, which was just to simply ask what the probability of being a given color was given you were an object or not an object, correlated with the surprisal. And the analysis is one of the coolest things I've ever seen, which is that objects, regardless of whether they're natural or artificial, tend to be warm colored. And the reason I like this analysis so much and found it so satisfying is that it speaks directly to this hypothesis that's permeating in the literature that's a kind of reconciliation of universalist and relativist claims. That is this idea that color terms don't reflect something about neurophysiology of conoponency or Haring's fundamental color psychological axes, or that it reflects something that you are trying to use that information to do. People have argued that, that this efficiency might be a representation of color space, and Regier might talk a little bit about that. I don't think that's quite the right angle to take that hypothesis. I think instead what it reflects is an efficiency to report on what you actually care about in the world that you're using color information for. So we went on to do a couple more experiments to test this idea that, that the color statistics of the world, that your color language reflects what you use color for. Ted came up with this genius experiment, a contrastive color test, in which he asked subjects with these pairs of objects to simply label what the color was. So he'd present one object and then another object right after it and just ask them what it was, and he pulled together 8 pairs of objects in which each member of the pair differed only in its color. It's a task designed to elicit in a natural way whether or not color is useful or not. And sure enough, the Chimani are loath to use color terms in this kind of task when you have these natural objects. English people use color terms more often, and they use them more often when they're presented with the second object. You can kind of imagine that. I show you a banana and it's green. You say, what is that? You say, it's a banana. And then I show you a ripe banana. You're like, oh, that's a yellow banana. It's like a sort of natural sort of thing to do. The Chimani, curiously enough, when the objects are artificially colored, then are prompted to use color terms spontaneously. And I find that extraordinary because it speaks to this idea I started with, which is that something about industrialization, the manufacturing of pigments, the way in which we have taken control over the chromatic statistics that we expose ourselves to, is now manifesting itself in the way in which they are using color language. So I just want to take a step back and sort of reflect on my own history as a visual neuroscientist. You know, a lot of people in visual neuroscience think that color is merely a low-level sensory stimulus used for detecting object boundaries, and that it is somehow inextricably tied to object shape. And they appeal to this idea of color memory. If I ask you what's the color of a banana, you all tell me it's yellow. And they say, see, yellow is inextricably tied to shape. Everything you need to know about the banana is in the shape. Color is just a low-level cue that's sort of attached on there. And this work, and some of the literature I'll get into in half a second, forced me to go back and say, actually, shape and color are decoupled. The banana shape does not change throughout its life that much, at least not in our house. We buy it, it's green, and then it goes through these various states. But somehow, unconsciously, when you're asked what color the banana is, what you go to is the relevance, the relevant color of that object to your behavior. And this is, you know, not news for anthropologists, as I learned when I went back and read some of the literature. This is from a Levinson paper in which he describes the black term, the origin of the black term in this Papua New Guinea language. It's related to this tree, but the tree isn't black, its bark isn't black, its leaves are not black. Nothing about the tree is black, except the nuts, when you roast them and you crack them open and you render them edible, they then have a black seed. So something about the behavioral relevance seems to be absolutely crucial for encoding the color of that term. And from a neural point of view, I find this compelling because it reinforces this conviction that I've had that if you really want to understand how to connect sensory signals to behavior and thought and action, color is perhaps one of the best ways of doing it. I'll stop in 4 seconds. You know, we often see, and I would be interested to know to the extent it is cross-cultural, but from the limited literature I've read on it, it does seem to be that we readily form associations, abstract associations of valence between color and their meaning for us. This is summarized beautifully in this chart that I found on the web. If you're starting out as a company and you want it to be creative, then use purple, because we've learned that purple indicates creativity, and MIT is red because they're nice and full of excitement, and the NIH is full of trust, and so we're blue, and so on and so forth. And it's in that spirit that I've now taken this work back into my lab to try and unpack how it is that we do this and how we do it in the brain. And in the last 2 seconds, I just wanted to turn my attention to an observation we made first in the monkey, showing that enormous swaths of so-called object cortex are involved in processing color, at least in responding to color stimuli. I showed these data to Nancy Canwish, who was like, well, that can't be true in humans. Let's test it. Maybe I'm mischaracterizing, but it was something along those lines. So since I don't know how to do human imaging, Nancy let us hang out for a while and taught us how to do it. And lo and behold, humans show through lots of this high-level visual cortex a similar arrangement that implicates a lot of extrastriate cortex in processing color. Now, I just want to return to saying color here is just a marker that allows us to uncover the functional organization. We don't need all of this tissue to process color. It's already done, we've shown, by V4. So what is this stuff doing? Well, I think maybe we might find it productive to think of the ventral visual cortex not as processing just what objects are out there in the world, but also in parallel something about what those objects mean to you. And that probably requires a lot of neural tissue. And with that, I want to thank you for your attention and the people who contributed. I think you go. It was only 22 minutes.
That was a lovely talk. I'm going to maybe broaden out a little bit from the question of usefulness. Of course, the question of culture, language, and color perception is a really old question. It's probably, language and color is probably the most investigated domain in the question of whether language shapes thought. It was one of the sources of the very first empirical tests of these ideas, and it remains one of the most hotly debated domains, so very appropriate for us to talk about it here. And a lot of wonderful work on this topic has been done by people in this room, including Terry Regier, for example, so you should take advantage of their expertise as well. I want to start with some big questions. First of all, why do we even see colors? Of course, we can make distinctions between objects based on shape and other properties. And the story that I have been told and that I dutifully repeat to undergraduates about why we see colors is that it's useful to have extra information. For example, you might be able to tell the ripeness of a piece of fruit in a tree without having to climb the tree, or it might be easier to tell a piece of fruit from the foliage because it would be distinctive by color. So in this array, for example, there is a pattern that is detectable by shape alone, but if I add color, it might be easier to tell what that pattern is, right? So this is a classic kind of demonstration of why you might want to have color. On the other hand, it's quite puzzling that deficits in color perception are very common in the population. So a rather large proportion of the male population has some kind of deficit in color perception. These weren't discussed or described in the scientific literature until quite late. So the first description I know of is this one by John Dalton. In fact, color blindness is often called Daltonism across languages. In 1794, he was a chemist, and he created a big stir by wearing a scarlet robe, scarlet academic robe, to an audience with the king. He was a Quaker, and this was seen as extremely scandalous. He thought he was wearing gray. It's surprising to me that it would have taken so long for someone to notice that here's a really large proportion of the population who does not experience color the way that other people experience color. So that should suggest to me that while color is useful, it's also obviously a private experience, but it's also maybe not as crucial as we sometimes think it is. And I'll let you guys argue with me. I think there is also a set of really complex questions in asking about language and color. So Bevel brought up the question of whether there is a word that is color across many different languages. But there's a further question you could ask, which is whether a language has color words. So color, of course, is one reflectance property of surfaces. To us, it describes some combination of hue, saturation, and brightness. But there are lots of other things that we get from looking at surfaces. So surfaces can look soft or hard, they can look glossy or matte, they can look cold or warm. And who's to say that in any language there should be a set of words that specifically talks about hue, saturation, and brightness as a compound, as opposed to all of these other material properties that we also get from visual experience. And the question of how to get this kind of information out of an interview with a set of respondents in a new language that you're not familiar with, I think is a complex question. Now, another question I think is interesting to ask is, what can you learn about color just from language alone? Suppose you had actually, of course we think of color as a completely visual, as this visual property, but suppose you had no visual experience, what would you know about color then? This is actually a question that Roger Shepard asked once. He was trying to map out color spaces, so he had people, he gave people pairs of color words and asked them how similar they are. So you might get a word like green and a word like yellow, and you have to say how similar they are in some scale, and then he would do some multidimensional scaling and create a space that would represent the similarities of those colors. And one day he had the idea, I wonder what congenitally blind people know about colors. So he went to the VA and he tried to get permission to study congenitally blind, I'm sorry, it wasn't the VA, it was a different hospital. He asked to get
have been designed or adapted for this purpose. And all I'm suggesting is that in creating languages, Mother Nature selects from the upper tail of that distribution. Now, in some respects, this is a kind of banal idea. It's sort of obvious, right? Like, why would it be otherwise? So, and it is, I think, in many respects, a sort of very simple, unassuming, and very familiar idea. But what I think is worth our attention, certainly it sort of grabbed my attention, is that this simple and unassuming idea explains a lot of data, much more than is traditionally given credit for. So, in particular, what I'm going to argue, and this, by the way, is a very old idea with roots in the functionalist tradition and some more recent work as well. What I'm going to argue is that this very simple and unassuming idea accommodates data from different semantic domains that have traditionally been treated separately, and explains a number of domain-specific generalizations from the literature within those domains. And in that way, I'm going to argue, this simple, familiar, and unassuming idea actually gives us a level of clarity and generality not previously available. So I'm going to try to convince you of that. And I'll do it first by examining color, which I'll try to go through quickly since we've already been warmed up very effectively on that. Thank you, Bevel. And then a few other domains, including kinship space and number. And then I will close out by engaging the notorious topic of words for snow. This is not a gratuitous insertion, by the way. It actually turns out to be relevant. So let's start with color. This is work with Paul Kay, Naveen Khetapal, number. So you are by now familiar with the standard color naming grid and the way in which it can be divided into categories in different ways across languages. This is a very famous example. This is the color naming system of Barinmo, spoken in Papua New Guinea, data collected by Debbie Roberson and colleagues in the late 90s, around 2000. This is a system which is rather different from English, but it's remarkably similar to many other systems that you can find, including some spoken in very different parts of the world. And so this is the sort of data that's generally taken as evidence for universal tendencies in color naming. That's half the picture. The other half of the picture looks like this. An amount of cross-language variation in color naming that I personally found quite arresting when I first encountered it. And so this is the sort of empirically mixed picture that we'd like to be able to account for. To do so, I'll invoke this notion, which is quite current nowadays, of informative communication. And again, forgive me, trying to make it cartoonishly clear. Imagine that there's a speaker who sees a color and would like to convey that experience to a listener who can't see the color but can hear the speaker. So the speaker uses a word, a color term, let's say red. At this point, it's the listener's job, if you will, to mentally reconstruct what she or he thinks the speaker must have had in mind. And if this view of communication, although simple, is at least broad strokes right, then what it suggests is that words should have meanings that allow accurate mental reconstruction by the listener of the speaker's intended meaning. So that sounds maybe plausible, I hope, in general intuitive terms. Let's try to formalize it so we can see how well it accounts for data. Assume we have a universe, and I'm going to be illustrating these ideas in the case of color, but they generalize to other semantic domains, as I'll be sketching very soon. So assume there's a domain universe. Here, the space of colors, shown for simplicity as a one-dimensional spectrum, although as you saw, the reality is more complex. And there's some specific target object in that domain T that we'd like to refer to. The speaker represents that target object as a distribution over the domain, tightly peaked at its actual location in the domain, and uses some word to express it. The listener then tries to infer what the speaker must have meant and constructs a distribution of her or his own. And then the critical question is how much information has been lost in transit, right? So we've had a communicative act here. As you can tell, the listener's distribution is a little broader, a little vaguer than the speaker's. That is to say, the listener does not understand perfectly, and we'd like to be able to quantify exactly what has been lost. To that end, we cast reconstruct target object T as simply the KL divergence between these two distributions. This is a standard of divergence between two distributions, especially when one is a sort of model of the other, which is the case here. We then take reconstruction error over the entire domain to be that quantity averaged over objects in the domain, where the average is weighted by need. So how often you need to refer to particular objects. And so in this sense, this is a usage-based theory. We then take informative communication to correspond to low reconstruction error. And the kind of bottom line here is that what this means we can do is take a given color naming system, like those that I showed you, and reduce it to a number, where the number is how much information we expect to lose on average when using this system. And what we can do then is optimize that quantity so as to create the theoretically optimal color naming system with 3 categories, 4 categories, 5 categories, and so on. This shows you the theoretically optimal color naming system, given all the assumptions I've just talked about, for 3 categories. And so a natural question is, are there languages that have color naming systems that look like this? And the answer is yes, roughly. Not perfectly, but roughly. We get similar results for 4. So this is the theoretical optimum for 4, a language that looks, you know, kind of ballpark like it. These are the results for 5 and results for 6. Now, what I personally have found kind of rewarding about this is that these ideas explain some known descriptive generalizations in the literature. So going back to Berlin and Kay, it's been known that this implicational hierarchy holds more or less. I mean, it's been updated since 1969, but more or less it's the case that if a language has 2 color terms, they will be roughly white and black. If there's a third, it'll be red, and so on, back through that implicational hierarchy. That order is explained by the ideas that I've just sketched for you. So here you see the optimal 2-term system, optimal 3-term, optimal 4-term, and so on, matching that chain. Now, many languages, and I think this is where it starts getting interesting, don't fit exactly. They're the other half of the picture, if you will. However, over all of the languages that we've examined, the 110 languages of the World Color Survey that Bevel mentioned, almost all are at least near optimally informative when assessed by this measure. And so I like to take this as suggesting that in this domain, at least, we have some support for this picture that I started with, that the semantic systems that we see may reflect a drive for informativeness in communication. Let's shift gears and examine a really rather different domain. I'm going to start with kinship. And this is joint work with Charles Kemp. Imagine there's a woman named Alice. And she has a daughter and a son and a daughter's daughter and a daughter's son and all the rest of a family tree. We can color code that family tree as you see here. This is in English, so the fact that MM, mother's mother, takes the same color as FM, father's mother, that is the case because we use the same word grandmother for those 2 kin types. You may not have seen the English system looking this way before, but my hope is that if you stare at it long enough, you ought to be able to convince yourself, yes, that's English. For contrast, and to give a sense for some of the, I think, really fascinating, by the way, cross-language variation in this domain, here is a different kinship naming system, that of Northern Paiute, an indigenous language of Northern California. You'll see that the mother's mother and the father's mother take different terms. The younger sister and the older sister take different terms, unlike English. But kind of intriguingly, and you can ask about this in Q&A, the daughter's children of either sex fall in the same kinship category as the mother's mother. So that, I think, there's sort of cool stuff lurking there. And so we can return to that. To test whether the kinds of ideas I've been talking about seem to apply to this domain, we considered a large data set of 487 languages from Murdoch. So this rests on work that many people have done over decades, and I'm immensely grateful to all the work that's gone into this. For our representation of the domain, we considered kinship grammars that were based on assumed universal primitives from the literature. So for example, our grammar for English, little sub-chunk of English, if you will, but specifically about family, looks like that, where mother is defined as parent and female, father as parent and male, and so on. It's pretty natural, I think. Need probability was something that we estimated by corpus frequencies in English and German. Ideally, I would like to get them in Northern Paiute as well, but that's a challenge. And I actually have been challenging my fieldwork colleagues to please come back from the field with something other than pronoun inventories. Give me some sense of the statistical environment that you've just marinated yourself in, because that's actually really valuable information for me. And finally, we explored in this work what I think is kind of an interesting trade-off between informativeness, defined exactly the way I did for color, and simplicity, which we take to be simply the compactness, the number of rules that it takes to define a system. So that gives us a 2D space, where informativeness is defined as before. So that's communicative cost, meaning low is good and informative. This is complexity, that is to say, number of rules in the grammar. Simple is good, and that's that way. What this suggests is that the ideal, the sort of the ideal communicative system resides at the origin. That sounds perfect, right? That's perfectly lossless communication for no cognitive cost. If that sounds too good to be true, it is, but I think it's useful because it's essentially mind reading, right? And I think what it highlights is that mind reading is the ideal to which language aspires but can never actually reach. And so what can language actually reach? It can reach those parts, that subpart of this space that you could get at by constructing a kinship system out of the material that we've been talking about. The gray dots here are the achievable regions of space. The black circles are the actual kinship systems from the Murdoch data. To sort of situate you, you are here, the red dot is English, and Northern Paiute is the yellow dot. So what you can see is that both of these systems and many others fall along the optimal frontier, or the Pareto frontier, trading off in a near optimal way informativeness and simplicity. And so the general suggestion that I'm pursuing in this line of work is that that trade-off, trying to trade off those two desiderata against each other, may be why we see the kinds of variation that we do in the world's languages, in kinship and other domains. I will briefly, frankly, merely claim that we have done similar work on spatial terms. Again, merely claim that we have done similar work on numeral systems, including, I think, an interesting link to the notion of recursion. Ask me about that later if you like. And my sort of interim conclusions for right now are that I hope to have convinced you so far that semantic systems of color, kinship, space, and number, the latter two merely asserted, the first two hopefully I've given you a little more than that, in the world's languages support efficient communication. And that what that suggests somewhat more broadly for me is that the wide but constrained variation that we see across languages may reflect adaptation to functional pressure. Now that, I think, at any rate, is a kind of interesting idea, but it's also a very slightly alarming one. And the reason it's a slightly alarming one is that there's a very high-profile example of the adaptation of a semantic system to functional pressure that's widely held to be debunked. And that is, of course, the vexed question of words for snow. And so with some trepidation, we went there. This topic is often introduced using this figure from Worf, but it wasn't Worf's originally, it was Boas's from 1911. Boas noted that in what he called Eskimo, there are distinct words for, that is to say, morphologically unrelated forms for falling snow versus snow on the ground. Worf picked that up, popularized it, and it pretty much went viral from there. As I think everyone knows, people started attributing absurd numbers of words for snow to unsuspecting Eskimo languages, which eventually led to a backlash, first by Laura Martin, then famously by Jeff Pullum, who dismissed the entire affair as an urban legend, the great Eskimo vocabulary hoax. Now, what I think is especially interesting about this is that despite all of the fuss and attention given to Boas's original example, remarkably little attention has been given to the central theoretical claim that his example was meant to illustrate, namely this causal chain. The character of the environment shapes local communicative need, which in turn shapes the category system of language. We wanted to test this. Now, it's hard to do so, and since it's a general claim, we'd like to test it using a large number of languages, which is challenging in the Arctic. There are only so many languages up there, and many of them are related to each other. But there's a way to get at this by approaching this in the opposite direction. I'll show you what I mean by that. If I were to type the word snow into Google image search, I'd get pictures like these. If I were to then translate that word into Arabic, I'd get this form, thalj, or telj. And if I were to enter it into Google image search, I'd of course get pictures of snow. obviously, but I'd also get pictures of ice. And the reason for that is that thelj is in fact semantically broad and can be used either for snow as on a mountaintop or ice of the sort that you plop in your drink to cool it off. So it should be immediately apparent that this is exactly the mirror image of Boaz's original snow example. Whereas he was arguing for semantic fine grain in this domain in a cold climate, here we're seeing semantic breadth in this domain in a warm climate. And the question is this coincidence? Or is it a reflection of something more general? We wanted to find out. And so we brought this causal chain into contact with data from several different sources. A standard climate data set to assess temperature where a language is spoken, Twitter posts in various languages to assess the frequency of mention of ice and snow in various languages, and the category systems. We just looked these up to note whether there was a single form for ice and snow on the Arabic model or different forms on the English model. Here's what we found. First off, languages that have different forms for ice and snow on the English model are found all over the place. So that seems at first like evidence against this hypothesis. However, languages that have the same form for ice and snow are found, on the Arabic model, are found exclusively in warm climates, and not just the same warm climate. They're found all over the place as long as it's warm. Those data are summarized up at the top. We found very similar results from another cross-language data set. Our Twitter analyses confirmed, I think very unsurprisingly, that ice and snow drop off, the mention of ice and snow drop off with mean temperature, but it's good to know given the amount of sort of assertion without data that's happened concerning this topic. And so essentially what I'd like to argue is that we do, in fact, have some support for this idea. So to wrap up, I hope to have convinced you that semantic systems across languages may reflect functional adaptation in support of efficient communication. And I hope to have convinced you that local communicative needs, despite the sort of disreputable feel about this claim, local communicative needs nonetheless may leave their imprint on semantic systems by modulating pressure for efficiency. I want to very quickly say that everything I've talked about today has concerned the influence of extra-linguistic forces, cognition and communication, on language. I'm also very interested in the inverse arrow, if you will. And I just wanted to very quickly mention that some colleagues and I have a take on the Sapir-Whorf hypothesis in terms of probabilistic inference, so inference under uncertainty, a view that we hold actually can resolve a lot of the controversy and tension surrounding that. So I won't say anything about that now, just wanted to put it up there. And I do want to acknowledge support by NSF and by the Berkeley Library, and warm thanks to my collaborators, especially Alex Carstensen, Paul Kay, Charles Kemp, and Yang Xu, and thank you for your attention.
So thanks, Terry, for a great talk. So I find the results from this talk and this research program very extremely compelling, and I think this is fundamentally the right way to start explaining sort of universal properties of different aspects of languages. And I think it's especially interesting because it's an explanation not just in terms of constrained formalism, but in terms of some outside variable. So the idea that languages are solutions to optimization problems involving outside variables involving the environment. So I'm going to talk about 3 topics related to this work, and this is really just a series of speculations and thoughts and extensions and so on. And first of all, I'm going to talk about this notion of the need distribution. So I think the really interesting part of these models, and the really crucial part for explaining variation, is this notion of the need probability. Probability that a language user is going to want to express some particular meaning or proposition or something like that. So crucially, in the work that we've seen, the need distribution is assumed to be stationary, meaning that it doesn't change over time. So you can imagine we have some need distribution, n of t, where t is the target, and you have some linguistic system or linguistic subsystem L. So we see that the language is sort of optimized in some sense for that particular need distribution. But if we imagine that need distribution is changing over time, so society is changing, the kin that we want to talk about, for example, might be changing. This is now moving around. And for the language, we're facing a very different kind of optimization problem when this is the case. And what I want to, think about is what are the potential consequences of the need distribution being non-stationary. So what it means is that instead of optimizing for our need at a particular time, we're going to optimize for what's our expected need in the future, given the way that we think the need distribution is going to be changing. Which is to say that exactly we don't want to overfit and hyper-optimize to a particular current need distribution. So we want to anticipate it'll change and optimize for some amount of robustness to changes. This is the trajectory by which the need distribution is changing and by which people think the need distribution is changing is a sort of interesting parameter of variation across cultures, which I think could be an interesting explanatory variable. So for example, our society is changing pretty fast, industrialized, because this cultures probably change faster than these sort of smaller population cultures that are spoken by a small group of people in a relatively stationary environment for a long time. You might expect sort of different linguistic properties for more industrialized cultures than these sort of smaller groups. I also think this notion of optimizing for some kind of robustness against changing needs could provide a alternative justification for the simplicity constraints that we saw. And so now I'm going to go to the notion of complexity. So the constraint of simplicity was important because it ensured that in this plot, so the communicatively good languages are this green strip, and the constraint of being simple means that we know that we're in the corner of this strip rather than being somewhere in the entire green strip. So the question is, I think, what's going on with these languages? And what makes them bad? And if just saying that they're complex is enough to say that we should rule those out. I think a lot of researchers are also uncomfortable with this notion of simplicity as an explanatory variable because it seems to depend a lot on the formalism in which simplicity is specified. So we saw, for example, that grammar over kinship systems, we could imagine maybe a different grammar that would have different complexity values for different systems. And of course, there's limits on the extent to which complexity varies across formal systems because of the Kolmogorov invariance theorem. But there's still a lot of freedom here which could become a researcher degree of freedom. And so simplicity can be a bit dodgy. But I wonder if we could accomplish the same kind of restriction, but by optimizing for robustness in the face of potentially changing need distributions. And I think there's good reason to think that these complex systems here, under small perturbations of the need distribution, these things might get wildly worse in terms of their informativity, whereas the simpler systems might be more stable. And the reasons for this have to do with basically the fact that what these systems are characterized by is overfitting. They're very complex systems which explain a very particular set of data. In machine learning, when we want to avoid overfitting and create models that explain a lot of data and generalize, what we do is we penalize the complex hypotheses or the lower probability hypotheses. So for the same reason that we use regularization and penalization of complex hypotheses in machine learning to get good generalization, we might want to have linguistic systems that are here in order to get good robustness against a changing need distribution. So this is all to say that languages might be adapted for a kind of robustness or anti-fragility against this need distribution. I also think that measuring robustness might not be so hard. So you can imagine you have a representation of the need distribution. You can imagine perturbing it and seeing what happens to potential linguistic systems. And I would conjecture, and it would be very interesting to test, maybe the complex languages are going to move around a lot under the changing need distribution. If that's the case, it could be possible to have plots like this without having to measure this using a particular formalism, which would be, I think, a relief for many people. So last I'm going to talk about some issues that arise when we imagine applying this logic to syntactic universals. So we have this issue of simplicity being defined relative to a formalism. The right formalism for syntactic simplicity is contentious, a little. That's pretty much all of linguistics. And so if the notion of simplicity ends up being based on this notion of divergence under perturbations in the need distribution, it might be possible to dodge this issue. But I don't know if that's going to work out. Another issue that arises is that for syntax, I wonder if the formal complexity of grammars is enough to reproduce the interesting patterns we see across languages. So I wonder if in addition to this informativity and its simplicity, we might also need a measure of the effort required for producing and comprehending utterances. So in the extreme, we can imagine a kind of degenerate example of an informative language with a very simple grammar whose utterances all take hours to say. And that would be a language that we want to sort of say is bad, but that's not going to be ruled out just by the combination of grammatical simplicity and informativity. So basically, to explain universals, the universals that have been posited to be explicable using this sort of processing efficiency stuff, we need to add processing constraints to this equation somehow. And I'm not sure exactly how to fit that in. As an example of a kind of phenomenon that has been explained this way, dependence length minimization can explain many of the syntactic universals across languages, and it appears to be motivated by a simple constraint for memory efficiency during parsing. Now, another issue, in studying syntax, we also get into potential issues with this idea of the need distribution. So the problem is it's unclear what the need associated with a particular sentence is, and what other sentences that fulfill that need or similar needs might be. So a simple way we might think of modeling is to say, okay, each proposition, each unit of propositional meaning is associated with some need probability. And then we'd argue that grammars create sentences that express useful subsets of propositions. The problem with that is that that's not going to work. So a particular communicative need, the reason that we talk, is really defined as the result in the world that I intend to bring about by talking. And it's possible to achieve the same result using multiple propositions. So for example, if I have the need of you closing a window, I could say, please close the window. That's one proposition. Or I could say, it's really, really cold. And that's a completely different proposition. And so it's basically not possible to associate propositions with the need distribution, I think, in a meaningful way, because the mapping from communicative intent to the proposition actually expressed by literal meaning is very complex. Another issue that arises with syntax also has to do with the flexibility. It has to do with this issue of the flexibility of the propositions you can use to express a particular communicative intent. So suppose a language makes it very difficult to express a certain proposition, like close the window. Suppose that's just really hard to say for some reason, or really complex. Using pragmatics, I could just say something else. And the result is that you could observe that languages, as used, appear to be highly optimized, when in fact what's not optimized is the language itself. It's just that in the particular utterances that people are saying, they're choosing the simplest way to say it. And so we have a grammar usage problem. It might be that usage is highly optimized without grammars being particularly optimized. Those are just some thoughts. All right. Thanks all.
Thanks, Richard. So there was a lot there. I'm not going to, I don't think, be able to respond to everything, but I do want to just touch on a couple of points. So need distributions changing over time, I think that's actually a totally fascinating idea. It's one we haven't explored yet. I guess I wonder to what extent we could, and I like the idea of, sort of optimizing both for current need and for anticipated future need. That's a sort of elegant thought. I wonder if we're sort of as a, I wonder if we're culturally savvy enough to pull that off, I guess is what I'm wondering. You know, there is a sort of notion of a cultural lag in which, you know, cultures change quickly, and sometimes a language will take a little while to catch up with something that has changed. But it's a sort of elegant possibility. And I do think the whole idea of shifting, basically shifting need is a sort of, it's cool. It's a cool idea. On complexity, I hear what you're saying about squishiness, basically, you know, Kolmogorov and so on notwithstanding. You know, even, yeah, I hear that. I sort of wonder whether we're going to be able to pull off what you suggested about sort of shoving it all off onto sort of robustness, if I understood correctly, basically. But it seems definitely worth pursuing. I want to flag that. Put your finger on something important, a way in which and now on to the third part of your talk where you're talking about processing constraints. I think one way in which the way we treat this notion of efficiency is actually a little different from the way many other people do, is that often efficiency is cast in terms of sort of effort of speaker in the act of speaking, which is what you were referring to. And in our case, it's effort that is, it's a cognitive load shared by speaker and listener by virtue of having to have a grammar in your head in the first place. So it sort of chews up space in here rather than sort of in the act of speaking. But yeah, I think that's actually an important distinction. So thanks for raising it.
Yeah, I wonder about. I'm actually addressing Rich's comment. When we talk about grammatical need, it's a little hard to reconcile with, say, the difference between English and Russian, where English has no cases and no gender to speak of, and Russian has, you know, 6 cases and 3 genders, and it's not clear that there's any difference in need there. Also, Dutch is an interesting example where there are 2 genders, but it's really hard for kids to learn because there aren't too many places where it gets marked. The German kids learn much more complicated system much sooner because it's marked more. And then we have, on the extreme, we have things like the Bantu languages with 15 to 19 genders, which are marked all over the place. So there's huge amounts of redundancy there. And you wonder what's the need that motivates that kind of thing. So I'm much more tempted to talk about need in terms of semantic distinctions that you make in categories than I am with grammatical properties.
So one sort of null hypothesis for the effect of need on syntactic properties could be that it's just very laggy, so that a language is optimized very slowly, and it takes a while to sort of work things out that are maybe inefficient. Another is that in terms of communicative efficiency, things like noun class systems and gender systems can be useful for robustness against noise, in that if you miss a noun but you've got all the gender markers, you can recover some information. And in fact, in straight up information theory, the kind of efficient codes they design in EE, the goal is actually to spread out information across the signal as much as possible, which is something that noun class system and genders sort of move towards a tiny bit. I'm also, you know, I'm not convinced yet. I'm just sort of suggesting this as a possible way to go. But it's not clear to me, that, given what I currently know, that it's crazy that syntactic things might be optimized.
You were on your feet first.
I actually don't think it's crazy at all that the syntactic stuff is optimized. I think that's right, but that's not what I wanted to ask about. I'm really interested in this issue that you two were just debating about whether it makes sense to think that we could be optimizing for future robustness. And I want to ask whether that's necessary, because I'm imagining, so here's just a thought example, and I haven't done the calculations, so I don't know, but say I'm playing a game of tag. So I'm it, and you know, you guys are running around the room completely randomly, right? My best bet is probably to be right in the middle if I can't move, right? If I was stuck and just couldn't move, my need distribution is constantly changing, right? Because I want to be wherever you are. If I can't move, I'd stick in the middle. Now, let's suppose, also it's probably what I would do if I knew I couldn't move and was trying to optimize for, you know, future need. But let's just say I move a whole lot less slowly than you do, and I'm always heat seeking. I probably still end up just jittering around in the middle, right? because I'm never going to be able to get that close to you before you've already moved. We also know, and we think that maybe languages actually are slower to change. We also know different parts of language are slower to change. So here's a prediction that you might look at. We know, for instance, that it's very, very hard to get new pronouns into a system. I suspect it's a lot easier to get new words for snow. So you might expect a stronger simplicity bias, say, in the things that are hard to get new ones of, like pronouns or gender marking, and a lot less of a simplicity bias in maybe some of the semantic domains that involve content words. A suggestion and a guess, but I'm curious what you think.
So you're saying if the need distribution is changing a lot, then an optimal solution is just not to move towards it.
Or I'm saying that that would be an optimal solution if I know that's the case. But let's say I don't know that's the case, but I'm just really slow, right? So I'm heat seeking, but because you're constantly moving, I end up getting sort of stuck in the middle because I'm constantly changing directions and don't get anywhere.
So it might be that the best generalization in the case of need that changes fast or languages that change slow is just that optimization is sort of damped down. I'm not entirely sure that, I haven't worked it out, but that seems like an intuitive prediction. Thanks for the suggestions. Do you have any thoughts?
What is heat seeking when we're,
so in my tag example, trying to move towards the person I'm trying to tag?
No, I mean like when we're talking about.
So I'm trying to be as efficient as possible. So this is like, so taking Richard's idea of trying to like not optimize for simplicity, but optimize for robustness. So I might, by trying to be too, being too informative, I may end up being in a problem that now I'm informative for a system I'm no longer interested in because the system I'm trying to describe has changed.
Yeah, no,
and this would, and so the heat seeking, I guess, on informativity, given, if that's where the heat seeking is, and it's just like what counts as informative is changing, that might result in a certain amount of simplicity, just because I don't have the option to overfit.
What's our time?
I gotta go, we can only go one more question. I'm sorry, there's other people working here. You could, we have one more question. I'm sorry. We have like people who have to leave who are who are employed, and we're way over time at this point. So.
Okay, so really quickly, that was great. And I had two comments/questions. One was about changing needs. And of course, we can think about communities and cultures having changing needs. But I wanted to prompt the idea that maybe the place at the individual level where the needs change most drastically is in the course of development. And so children enter school, and the need to talk about things is enormously different. And I wonder about the predictions that one might make there. I don't expect you to be able to answer that, but I think it's an interesting way to test some of that potentially, though I don't have it worked out. And the other comment, still speaking very quickly here, is to encourage the thoughts about processing demands, of course, in inefficiency, but also consider the relative burden of production and comprehension, because they are not the same and they vary with respect to, for example, long distance dependencies versus choice of lexical items, and just really working through some of that at a finer level than the computational level, I think is going to be, I hope, is going to be really useful. Okay, thanks.
Thank you.
Thanks.
I mean, thanks very much.
Okay, I don't have anything else to say. Thank